good morning and welcome everybody to our final session. Can you believe it? These 3 days have flown by. Session number 3 of 3 in our CCNA Foundations course. And you might notice that the background behind me is a little bit different today because I mentioned yesterday that the main computer that I instruct from, it was on the fritz. It was crashing pretty regularly. So I thought, okay, I've got another system, a backup system. I've got a backup microphone and everything in my main office. So that's where we're teaching from today. And that's sort of a great segue into one of our topics today, which is on redundancy. Redundancy is huge because in some organizations, if your network goes down, it's not just inconvenient, it's super expensive. Can you imagine how much money Amazon.com would be losing if their network went down for 5 minutes? I cannot fathom how many sales that happen in 5 minutes. That's just one of the topics coming up today. We got lots of fun topics coming up today, and we're going to be giving away sort of the grand prize today at the very end. So if you'll stay with us, on day one we gave out Todd Lamley's Cisco Networking Technologies book. On day two, we gave out the CCNA Certification Guide, really thick book there. And today, the grand prize, I've got another set that Todd sent over, and I'm going to be giving you the entire set. So both books, the entire library for our grand prize winner today. And Charles is going to be selecting someone in the background. I told him to look for somebody that's really participating and just kind of being a good citizen in the community, maybe helping each other out, just really engaged. So he's on the lookout. So be on your best behavior. Well, let's get into the official topics for today. And first up is a continuation of yesterday. We left off talking about routing and some of the theories surrounding routing. We talked about different ways that a router could learn its routing table. How does it know how to get to a route? We said we might be directly connected. We said that we might learn it via a routing protocol or through redistribution or through a static router configuration. Well, we're going to focus on a specific routing protocol right now, and it's OSPF. A little backstory. In previous versions of the CCNA, in fact, let's talk about the previous version, the CCNA that was active January of this year. On the blueprint, here are the routing protocols that you needed to know about. You needed to know about, from the blueprint, EIGRP for IP version 4, EIGRP for IP version 6, RIP version 2, OSPF version 2, OSPF version 3, and BGP. BGP was on the CCNA. That blew a lot of people's minds. But there's just one. On the new blueprint, they've really trimmed it back and they focus on one, and I would argue the most popular protocol out there today, and that is OSPF version 2. In fact, quick survey, if you know and if you don't mind sharing. I don't want you to give away corporate secrets or anything, but this is a question I've been asking my students for years. Would you mind if you don't want to tell me, that's fine. I don't want you to do something you're not supposed to do, but if you don't mind sharing, I'd love to know, what is the primary interior gateway protocol running in your company? Is it RIP? Hope not. Is it RIP? Is it ISIS? Is it OSPF? Is it EIGRP? Is it static routes? Are you running IBGP for within an autonomous system? Let's see. Lots of votes for. Looks like OSPF taking the lead here as I'm looking at the chats roll in. Lots of EIGRP out there. Awesome. We'll talk about that today. We've got some ISIS. Awesome. Fantastic. Thanks for the feedback. All right. Well, let's get into the discussion of the primary protocol that's on the new CCNA exam, and that is OSPF version 2. Now, version 2 means we're routing IP version 4 networks. OSPF version 3 would allow us to route IP version 6 networks. But here, we're going to focus on IPv4. And I'll give you just a little discussion about EIGRP and BGP because I want you to have more of a broad foundation. That's what this course is all about. I want to give you a foundation for your study. So I don't want you to know about just one routing protocol. I want you to know about a few of them. But primarily, we're going to focus on OSPF version 2. And I pointed this out yesterday. I said that OSPF was kind of unique. It was a link state routing protocol, and that meant that it had a map of the topology. Just like your navigation system on your car or your smartphone. It was able to run. Anybody remember the name of the algorithm that OSPF would run and your car's navigation system would run? Bonus points if you get the spelling right. What algorithm did we run? And it would assign a cost to every, your navigation system assigns a cost to every roadway. Lower cost is better. Well, OSPF is going to assign a cost to every link. Oh, yeah. Correctly spelled Dykstra. Awesome. Y'all are all over it. Oh, somebody just noticed that, yeah, I've got a Mickey Mouse in the background. Yeah, that's actually a Mickey Mouse phone. I don't know if you can tell that. And this is a, let's see right here. This is a Thomas Kincaid Beauty and the Beast poster. If you didn't know, I'm quite the Disney fan. We talk about that a lot in my classes. But the router has a map of the network. And speaking of Disney, it reminds me of this puzzle, this Disney puzzle that my daughter and, well, now her husband, well, they were working on this a few months ago. And I saw this puzzle and I said, okay, I got to take a picture of this for my OSPF students. And they're like, you want to take a picture of this puzzle for your what? So I gave them the explanation that I'm about to give you. When I think of OSPF routers putting together this map, it's like 2 or 3 people working together to put together a puzzle. That's a very accurate metaphor. Because think about it. If you're working on a puzzle like this, you've got your collection of pieces in front of you, your neighbor's got a collection of pieces in front of them, and maybe you've got a third or fourth person working. They all have the pieces that they're looking at, that they're directly in front of, that they know about. And together, you collaborate and you try to put this puzzle together. You put a piece here and a piece here, and you squeeze in anybody say, yeah, does anybody have Cinderella's slipper? And somebody does, and they give it to you, and you plug it in. And after a while, through everyone's contribution, you have a complete picture of the puzzle. That's what OSPF does. Routers are connected to different networks, and they collaborate with one another, and they say, hey, I'm connected to this network, and I'm connected to this network. They collaborate and put that information together, and they form a map of the network on which we can run the Dijkstra algorithm. There is some terminology that I want you to know, though. First of all, we're going to talk about EIGRP, which is technically an open standard, but OSPF is a very open standard. You see that in a lot of environments. And we're going to establish a conversation with our neighbors. We're not going to do like RIP did. We talked about RIP last time. RIP, just remember, every 30 seconds, it would just broadcast or multicast out and say, hey, here are all the networks I know how to reach. It didn't speak to any specific router. It just send it out to anybody that would listen. But with OSPF, we establish conversations or communication paths with what we call a neighbor. And we're going to distinguish between a neighbor and an adjacency. They're not the same thing. And the way that we build this puzzle is like we're exchanging puzzle pieces. Think of a piece of a puzzle like an LSA. An LSA is a link state advertisement. That's a piece of the map of the network. Now, for your notes, what we call that map, it's called the link state database. The link state database is a map of the network. And in your CCNA, and if you join us for Encore and an RC, we get deeper and deeper, and we fully explore that link state database. It's a pretty interesting. There's a lot of moving parts in there. But for now, just think a puzzle piece is a piece of information. An LSA is a piece of information that can be combined with other LSAs to build the map of the network. And we're going to run the Dijkstra algorithm on that completed map of the network. And OSPF is going to say, here's a list. OSPF is going to build, here's another term for your notes. OSPF is going to build what it calls a RIB, R-I-B. That stands for Routing Information Base. If we had EIGRP running on the same router, it would build its own RIB, its own route information base. But here's the point. Just because OSPF knows how to get to network 20.1.5.0/24, that's no guarantee that it's going to be placed into the router's IP routing table. Why not? If OSPF says, hey, here's how to get to this network, why would the router not add that to its routing table? And the reason is there might be a more believable source. We'll talk about it in your CCNA studies for anybody joining us next week. We're going to talk about something called the administrative distance. That's the believability of a routing source. And we're going to see that directly connected networks are most believable. Statically configured networks are slightly less believable. And EIGRP networks, they're next on the list. A little less believable are OSPF and then ISIS and then RIP. And yeah, if there's a more authoritative routing source, we might not listen to what OSPF is telling us. So just keep that in mind. It's not a guarantee that we're going to be putting that in the link state database. Some terminology that we've got to know when we talk about OSPF. The way these neighbors talk to one another is they say hello. They send these hello packets to a multicast address. The multicast address is going to be 224.0.0.5. And that multicast address, that's sort of a well-known multicast address that goes to all OSPF speaking routers. And that's how we form a neighborship and how we exchange information. And the information that we're going to be exchanging, I say we exchange information. I don't mean route information. I mean we exchange things like our MTU size. We talked about that earlier on in the week. We exchange parameters about us. Here's how we're prepared to talk to you. And once they agree and they form this neighborship, then they can start sending the route information. Now, I said that an LSA was a piece of information that was going to be sent out, and everybody's sending out their own LSAs, and we're going to build this map of the network. Well, when we do that, we're going to send packets containing that information. And here's where a lot of people use the wrong term. So please hear me on this. This is a super common mistake that a lot of people make. A link state advertisement, an LSA, that's information. The packet that carries that information is called an LSU, a link state update. So remember, the packet, if somebody says, I'm receiving these LSA packets, no, you're not. You're receiving LSAs, but they're inside of LSU packets. So just a little terminology trip that many people fall over. So I wanted to make sure you were clear on that. Now, sometimes a router is going to build a map and its neighbor, it's building a map. In the end, everybody should have an identical view of the network. Everybody should have the same link, a matching link state database. But I mean, things happen. Packets get dropped. We might have a situation where a router says, uh-oh, I'm missing a piece to the puzzle. Remember the Disney puzzle I showed you a few moments ago that my daughter was building and her husband were putting together? Well, they had lost a piece of the puzzle. They'd worked for hours and days, and it's like, where's this piece? And I looked around, and sure enough, it was on the floor, and it was turned upside down. So the brown on the back of the puzzle piece matched the brown of the floor. It was really difficult to see, but I got to be the hero that day, and I found the missing puzzle piece, and we put it in. That's what an LSR does. An LSR says, hey, I'm missing a piece to the puzzle. I'm missing part of my link state database. Does anybody else have that? And if somebody else does, they will tell us. They'll respond with a link state, excuse me, I didn't mean to advance that too quickly, but it was a link state acknowledgement saying, all right, here you go. A link state reply, and then we acknowledge that. So that's how we build a link state database. Now, I mentioned that there's a difference between an adjacency and a neighbor. This is another common point where people use the wrong words all the time to describe this. There's a difference between a neighborship and adjacencies. There's a difference where we in how much information that we're exchanging. For example, a neighbor, two neighboring routers, they're going to. Oh, by the way, I'm seeing some people saying that they're having an issue hearing the chat sound. There's a way to mute that. Let me see. I think there's something I can do really quick here to fix that. Thought I'd already done that. A second here. Yep, I will mute the sound for you. That should have fixed it right there. Sorry, I thought I had already done that. But you shouldn't hear it anymore. But back to the story. A neighbor just tells the neighbor hello, and that's it. They're not exchanging information. An adjacency, they not only say hello, they're not only neighbors, they do exchange information. As a metaphor, we're going to think of my situation. Here where I live, I've got two neighbors, and I only have two neighbors anywhere near me. We're out in the country a little bit. I mean, we're on 5 acres right here. We don't have nearby neighbors, but there are two neighbors that live down the road from me. And one of them, I would say, is just my neighbor. Honestly, if I met them in public, I probably would not recognize them, I'm ashamed to say. But I know what they drive. So as I'm pulling out of my gate and they're going by, I wave at them, I say hello. We say hello to each other, but we've never really had a conversation. That's just like OSPF. They say hello to one another, but they don't exchange any information. Now, my other neighbor, we've been to their house, they've been to our house, we've worked on a project or two together, we text, we call, we exchange a lot of information, we have a tighter relationship. So that's like an adjacency. An adjacency is going to exchange information. So it's going to be sending those LSUs. But neighbors, they've got to reside on the same link. They're going to send those hello messages back and forth. Adjacencies are neighbors. That's a prerequisite. But they have exchanged information. They've helped one another build this database. Now you might be wondering if an adjacency will provide all of this information, why don't we make every router adjacent with every router? It seems like that would be more information. Wouldn't that be a good thing? Well, it doesn't scale terribly well, unfortunately. Let me give you an example. Now, this is a simple network with only 6 routers. But imagine if I had an adjacency between every router. That's a lot of adjacencies. Here's the formula. It's n times n minus 1, where n is the number of routers. N times n minus 1 divided by 2. So we've got 6 routers. So 6 minus 1 is 5. 6 times 5 is 30. Divided by 2 is 15. We've got 15 adjacencies here. Not horrible, but what if we had 10 routers that had interfaces on the same subnet as these do? 10 times 9 divided by 2, 45. We'd have 45 adjacencies with only 10 routers. It doesn't scale well for everybody to be adjacent with everybody else. So what do? Well, we designate a router to sort of be the keeper and reiterator of LSA information. We send it to that router, not everybody else, but we send it to that designated router. That's what it's called. It's called a designated router, or a DR for short. And that DR is going, let me back up a slide. That DR is going to then send the information that you send it. It'll send it to everybody else because everybody has formed an adjacency with the DR. But what if the DR goes down? We're kind of dead in the water. So there's a backup designated router, a BDR, that we also elect. And yeah, in the CCNA class, we get into exactly how that election happens, how you can influence it, there's a bunch of stuff we can do there. But I want you to know for now the terms. The designated router, everybody forms adjacencies with that, as well as the backup designated router. And we are dramatically reducing the number of adjacencies that we have to form. And you might be thinking, well, when I send out my information, here's some LSA information sent in LSUs. Remember, that's the packet type. If I send it to 224.0.0.5, doesn't that go to all OSPF speaking routers? Check this out. If we have elected a DR and a BDR, we'll send our OSPF information to a different multicast group. We're sending it to 224.0.0.6. That only goes, or the only members of that group are the DR and the BDR. So that will dramatically cut down on all the chit-chat, if you will, on a really large network. And this is when we have multiple routers sharing a common subnet. Sometimes you've just got a point-to-point router. You've got one router going directly to another router. Yeah, there's no need for a DR. So a DR is not always elected, but when you have some sort of like an Ethernet network where you can have multiple devices on that segment, yeah, that's where you start to need your designated router. And we said that the Dijkstra algorithm, and again, if you want to go into the math behind how the Dijkstra algorithm works, I've got a YouTube video on that from a few years back. Just search on YouTube for Kevin Wallace, Dijkstra, D-I-J-K-S-T-R-A. And that'll give you a really mathematical view of how the Dijkstra algorithm works. But I would put many of you to sleep if we started talking about the Dijkstra algorithm this early in the morning. But let's talk about how OSPF will assign a cost that is then used by the Dijkstra algorithm. Here, let's say that PC1 wants to get to PC2. And there's a couple of ways we could do that. It could go up to R1, it could go over to R3, and then out to PC2. An alternate path would be we could go from R1 up to R2, down to R3, then down to PC2. Now, RIP that we talked about yesterday, remember how it was a distance vector? Remember how it measured the magnitude of that vector? It was hop count. How many routers do I have to go through? Well, RIP would say, well, I've got to go out of router R1, and I got to go out of router R2 and R3. That would be a cost of 3. That'd be a cost of only 3 hop counts, or that would be a cost of 3 hop counts. But what if I went from R1 to R3 and then out? That's a cost of 2. We would say if we were running RIP, obviously we're going to go directly to R3. Why in the world would I involve another router in this? It's another hop. But OSPF says, not so fast, RIP. You're not considering the bandwidth. If you look at the bandwidth, that link between R1 and R3 is a measly 10 megabits per second. All the other links are 100 megabit per second links. So what we're going to do with OSPF is assign a cost. And the formula for calculating the cost is to take OSPF's reference bandwidth and we divide it by the link speed. Now, by default, the reference bandwidth for OSPF is 100 megabits per second. So let's assign some costs. What would be the cost of that 100 meg link as we go out of R1 up to R2? Well, the reference bandwidth is 100 meg. The link speed is 100 meg, so 100 divided by 100 is 1. Same thing as we exit R2, that's a cost of 1. As we exit R3, going down to PC2, that's another 1. That's 3. It'd be a cost of 3 if I went from R1 to R2 to R3. If I went from R1 to R3, what would be the cost? Well, here the reference bandwidth is 100 meg. The link speed is 10 meg. That's 100 divided by 10. That's 10. And then it's another cost of 1 to go out of R3 down to PC2. That'd be a total cost of 11. So OSPF is going to disagree with RIP. OSPF is going to say, no. I think it's going to be much more efficient if I go from R1 to R2 to R3 to go out. That's the way that OSPF does its calculation. But I've got some really bad news. There are a lot of network administrators out there that have a false sense of security that OSPF is picking the lowest cost path. And it's not. Why? It's that pesky default reference bandwidth I told you about. Remember I said the default reference bandwidth, and we divide the link speed by that reference bandwidth. I said it defaulted to 100 megabits per second. What if we had a gig link? That's 1,000 meg. What is 100 divided by 1,000? It's 0.1, but we cannot have decimal values when it comes to cost. It has to be an integer. So we would say it's actually a cost of 1. The point is, by default, OSPF is going to view 100 meg links as a cost of 1, gig links with a cost of 1, 10 gig links, 40 gig links with a cost of 1. That 400 gig interface I showed you the other day would also have a cost of 1. That's horrible. So my strong recommendation is that you consider carefully changing your default reference bandwidth. And when we get into the config in the CCNA course, we talk about how to do that. But yeah, what I do personally, I like to set my default reference bandwidth to 2 terabits per second. That way I'm good until I'm going to treat all these speeds differently until I get past 2 terabits per second. Now, I say all those speeds. If I have really, really low speeds at that point, if I've got like 64K links and 128K links, yikes. But if I set my reference bandwidth too high, those start to have the same value. It's based on the number of bits that you can have in the cost value. But yeah, if you go too high, your lower speed links look the same. If you go too low, your higher speed links look the same. So do what's right for your network. Yeah, I can see 20 years ago that might have been a perfectly reasonable reference bandwidth. It's not today though. Again, I like to set mine to 2 terabits per second. And when we think about OSPF and we think about building these maps, I said we're going to have a map of the network. Let me be a little bit more specific about that. We're going to have a map of an area. We can take a really massive OSPF network and we can logically divide it into different areas. And here we've got an area 0, and all these routers in area 0, they have an identical map. They've got a map of area 0. But if I wanted to break my network up, if I added some routers, we might have multiple areas. Here I've got area 0, area 1, and area 2. By the way, requirement side note, if you do have more than one area, you must have what is called a backbone area, which is numbered area 0. And every other area must touch directly. It must touch area 0. So area 1, area 2, notice that they physically touch area 0. Now, there's a little workaround called a virtual link that we won't get into here, but yeah, you need to touch area 0. But with 3, you know what? I just noticed that what we were talking about my affinity for Disney. I think I might have drawn a Mickey Mouse head when I was drawing my areas. That was not intentional, but it sure looks like that. Area 1 has a map just of area 1. Area 0 has a map just of area 0. Area 2 has a map just of area 2. So how do we, if I'm in area 1, how do I get to a network in area 2? I mean, do I say, give me a map of area 2? That kind of defeats the purpose if I've got to look at everything. Here's what we're going to do instead. Notice that we've got a couple of routers that are sitting at the boundary. Notice that router R3 and router R7, they're called ABRs, area border routers. Here's the definition for your notes. Oh, somebody said I'm a hidden cast member. Not hidden. Here's actually my little here's my little cast member pin from back in the day. But those routers, those ABRs, they have a database for every area they touch. So R3, it's got a map of area 1. It's got a map of area 0. How does it tell area 1 about area 0 networks? It's not going to say, here's the map, because that would defeat the purpose of having a smaller map to run the Dijkstra algorithm on. It's simply going to tell area 1, hey, here is a listing of key point here. This is a listing of networks that you can get to. If you want to get to any of these networks, come to me. Don't worry about how. We're going to get there. Give it to me. I'll get you there. So that's the difference. The area border router is going to give a listing of the networks available outside of an area. It's going to give that listing into that area. And if they want to get to one of those networks, they just go to the ABR and it handles it. It's got a map. It's got a link state database. Now you might be wondering, okay, should I break my network up into different areas? The Cisco has a recommendation that I'm afraid some people are still using today. The recommendation was made back in like the mid-1990s. And the recommendation was, if you have more than 50 routers in an area, you should create a second area. Every 50 routers, create an additional area. And the idea was, we don't want to put too much processor burden on the router's processor by running that Dijkstra algorithm. If we put too much processing demand on it, it's going to slow the router down. We're going to have bad performance. We're going to start to drop packets. So they said, we don't want to overtax the router. Let's not have a database containing more than 50 routers. That was mid-1990s. In fact, the router that they base this on, I don't know if anybody remembers a router this old, but it's the old Cisco 2500 series router. Actually, I just thought, I actually have one right now. I still use mine. I use it as an access server. I go to it to connect to the console ports of other devices. But yeah, I've still got one. But it's not a racehorse. It's slow. It has a very weak processor by today's standards. I mean, today's routers, we had the ISR routers like the 2800s. We had the second generation like the 2900s. We got the third generation of ISR routers like the 4000 series. Those are orders. They're not just a little better. They're orders of magnitude better than the old 2500 series processor. So I would have zero hesitation running, well, Disney, for example, I said we had about 600 routers. I'd have zero hesitation running, okay, I might hesitate a little bit, but I'd have almost no hesitation running one area for all 500 routers because today's routers can handle it. It's not a big deal. Is there a time I would personally break a network up into different areas? There is. And one reason is not for the network's benefit, it's for my benefit. If we have a data center, if you have a really complex data center and you've got lots of different departments, lots of different customers, you've got a lot of networks. sometimes you have thousands, no kidding, in some data centers you have thousands of different network address spaces. You run out of VLAN numbers and you have to start using something called VXLANs that we talk about in the Encore course. But it's a lot. If I'm troubleshooting the enterprise network, I don't want to have to wade through the thousands of networks over in my data center. I just want to see what's in the enterprise. So just to keep things simpler for me, I'd probably put the data center in its own area. There's probably one or two other reasons, but that's the first one that comes to mind is, yeah, if I've got a data center, just for my own troubleshooting and monitoring purposes, I don't want to put that in its own area. Now let's shift our focus to EIGRP, and we'll take a little Q&A break after we talk about these different routing protocols. Now EIGRP, we had a lot of people when I asked you at the beginning of class. We said, what routing protocol are you running? I think OSPF was the winner. They were flying by really, really quickly. I think OSPF was the winner, but a close second was EIGRP. And I'm a huge fan because not only does it converge really fast, like OSPF and EIGRP, they converge at like 2 or 3 seconds. In other words, your primary path goes down. It can reroute around to a backup path in just like a couple of seconds, while RIP might take 3 minutes. So it's got very fast convergence, and it will scale. It is very scalable. And to make the point, at Disney, that is the protocol that we used. We used EIGRP on about 600 routers, and it worked beautifully. So it's very, very scalable. And it's not just scalable. We can do something that no other routing protocol can do. We can load balance across unequal cost paths. Remember when we talked about an ether channel the other day with switches? We said we could logically bundle together these physical connections, and it would look like we had this fatter bandwidth pipe that we could push data through. This is kind of like that. We might have two routers that have two connections between them. Not routers, not switches, but routers. And one might be a slower link that's just there for backup purposes. If the primary link fails, we'll fall over to the backup link. Oh, by the way, if they were the same speed, OSPF would say, hey, I got two paths. I'll load balance across those equal cost paths. But if one is faster than the other one, OSPF says, no, I'm just going to use the fastest one. EIGRP says, I don't want it to just go to waste. I know it's got lower bandwidth, so I'll not send as much traffic over that lower speed link, but I'm going to send some. I don't want it just to be like dark fiber that we talked about the other day. So it will proportionally send more traffic over the higher speed link, but still some traffic over the lower speed link, and we get load balancing across unequal cost paths. That is a feature that's called variance. We talk about how to set up variance in the Encore course. And the way that we're going to, it will use advertisements that do include the subnet mask. Almost don't think it's necessary to mention that because almost every routing protocol today does advertise subnet mask information. OSPF does, EIGRP does, recent versions of RIP do. The reason I guess I bring it up is RIP version 1 did not. It had to be a classful network. And it's going to communicate to the multicast address of 224.0.0.10. So if you just want to make a note for your own reference, not really something to study, but for the real world, we've been talking about these different routing protocols and the multicast address that they send their information to and their hello messages to. If they have hello messages, if you want to write them down real quick, RIP version 2, it's 224.0.0.9. All of these are going to begin with 224.0.0. But RIP version 2, 224.0.0.9. EIGRP, as we see here on screen, it's 224.0.0.10. OSPF has a couple. OSPF has 224.0.0.5 that goes to all OSPF speaking routers. And it's got that other one, 224.0.0.6, that just goes to the DR and to the BDR. And until about 2010, EIGRP was Cisco proprietary. At Disney, it was still, when I worked there, it was still Cisco proprietary. So we had an all Cisco shop. Our switches, our routers, they were all Cisco, and it worked beautifully. But around 2010, I think I mentioned this in a previous session, there was a there was a movement to make EIGRP sort of an open standard and open it up to the industry. So Cisco said, we know we've got this awesome routing protocol that we developed. I'm sure other people would like some of this, so we're going to open it up a little bit. So they began by opening up some EIGRP features to the industry. And the industry basically said, no, we're good. They had very little desire to adopt EIGRP. So then Cisco said, okay, you can have all the features. And they pretty much made it wide open so any vendor can adopt the EIGRP features and put it in their equipment. And there's been some adoption. I'm trying to think about, I know of about 2 or 3 examples, but that's about it. And a lot of those examples are just so you can migrate from Cisco gear onto their gear. So if you're using EIGRP, usually you're in an all Cisco shop when you're doing that. Now let's talk about how EIGRP makes its path selection. It is going to assign a metric, and we'll talk about how that metric is calculated in a few moments. But it's going to assign a metric or cost to each of its links. But remember, unlike OSPF that has a map of the entire topology, EIGRP does not have that luxury. EIGRP has to learn what its next hop is. It's a distance vector routing protocol. Yes, I'll give you that it's an advanced distance vector routing protocol, but still, it's a distance vector routing protocol. It knows magnitude and direction. It knows here's my next hop and here's how far. Here's the metric to get here. But one of the things that makes it advanced, it doesn't just wait. It doesn't wait for the primary link to fail and then say, well, I better find a backup link. No, it tries to have another backup link on standby. That's one of the reasons that it can cut over so quickly in like just a couple of seconds. So here's what it's going to do. It's going to listen to its neighbors. Its neighbors are going to say, here's how far we are from your destination network. Take R3 on screen, for example. R3 wants to get to 10.1.1.0/24. And it looks like we've got two options. R3 says, or R1 says, I'll get you there. R2 says, I'll get you there. And you'll notice the metric of R1 and R2, they're the same. R1 says, I can get you there in a metric of 1,000. R2 says, I can get you there in a metric of 1,000. And they both report, keyword, they both report their metric to R3. In fact, here's a term for your notes. The information given to us by our neighbors, their metric, that is called the reported distance, or the RD. Sometimes known, as I'm using on this table, sometimes known as the advertised distance, or AD. So you might hear those terms used interchangeably, reported distance or advertised distance. But then R3 says, okay, it looks like they're equally close to the network I want to get to, but I've got to get to them first. What's the cost? What's the metric of me getting to them? And we look at this, and it looks like we've got a pretty slow serial link getting down to R1. We say that it's a cost of $10,000 to get to R1. It's a cost of $5,000 to get to R2. So let's add it all up. What's the grand total cost to go via R1? It's going to be 10,000 plus 1,000 for a grand total of 11,000. If I go via R2, it's going to be 5,000 plus 1,000 for a grand total of 6,000. So clearly, R2 is the way to go. But if that link to R2 or somebody pulled the plug out of R2 and it just went down, EIGRP would say, okay, I'm ready for this situation. I've got somebody on standby and they're going to take over. Here are the terms I want you to put in your notes. The router that we're using, or the path that we're using, is our preferred primary path. That's called, for your notes, that's called the successor route. The successor route. That's the preferred route. But R1 in this case, it's a way to get us to that destination network. We're not using it yet, but it's a way to get us there. The term for your notes is, it's called a feasible successor. So a feasible successor is the router, a feasible successor path. That's the backup path that we're going to be using. But the successor router, or the successor path, that's our preferred mechanism. So that's how EIGRP is going to learn. It's going to get that reported distance from its neighbors, and it's going to make a path selection decision based on that. And there could be an issue here. because EIGRP is at somewhat of a disadvantage compared to OSPF. Because OSPF, again, it's got the map of the network. It knows how everything is interconnected. It knows that this router goes to this router. But with EIGRP, we don't have the luxury of knowing that. With EIGRP, let's say that R1 says, I'll get you there, but it costs me $7,000. Okay, do we still want it to be our backup path that we're going to cut over to almost immediately? Maybe not. The reason I say that is the way R1 got to our destination network, for all we know, because we cannot see the network, it's going to get to that destination network via R2. So if R2 goes down and we say, no problem, we've got R1 on standby. No. R1 was dependent on R2. Your backup died at the same time your primary link died. In an effort to prevent that scenario, Cisco has, or EIGRP has, a feasibility condition. I'm going to read it. It's going to sound uber confusing, but then we're going to explain it. But here is the feasibility condition. You might want to take a screenshot of this. Or if you've already signed up for CCNA, this will be in your notes later today in your portal. An EIGRP route is a feasible successor route. In other words, this route can be a backup route if and only if the reported distance from that neighbor is less than, not equal to, but less than the feasible distance of our successor route. Let's go through an example together and put some numbers with this and make it make a little bit more sense. Let's take a network where we've got R1 wanting to get to network 10.1.1.0/24 over on the right-hand side of your screen. There are 3 ways of getting there. Now, you and I can look at this topology and say, oh, all 3 of these routes, R2, R3, R4, they're both capable of getting us there. There's no loop. R4 is not dependent on R3 to get us there. But EIGRP doesn't know that. For all EIGRP knows, R4 is not connected directly to R5. R4 is connected to R3, and that's the way it knows how to get to 10.1.1.0. R1 doesn't know how they're interconnected. That's the disadvantage. So in an effort to make sure we don't have those backup paths which are dependent on our primary path, we're going to use this feasibility condition. So to make sure you understand it, because I admit, the way that thing's written, it's not like, oh, I get it. No, you don't just get it by reading it one time. So let's go through a few examples. R1 is going to say, I want to get to 10.1.1.0/24. Let's take a look at the best way to get there. Oh, I've got these 3 neighbors that are saying, I'll get you there. R2's telling me, R3, R4, they're all saying, I'll get you there. So let's look at their reported distance. What is their distance to get to this network? Well, if you do the math and look everything up, you're going to see that it's a cost of $6,000 for R2 to get there. It's a cost of $11,000 for R3 to get there, and it's a cost of a whopping $18,000 for R4 to get there because it's going over this really slow serial link. It still could be a backup path if the other 2 routers fail, but EIGRP doesn't know that. So EIGRP says, all right, what is my distance to get to each of those routers? We got to add all those up. And I won't read through all the numbers. You see it on screen. But the shortest feasible distance, the total distance, is 16,000, and that's via R2. So that's our preferred path. That's our successor route. And we say, R3 can also get me there, it says, but only if it meets the feasibility condition. Well, I just immediately fail over to that. Here was the criterion again. The reported distance from that neighbor must be less than the feasible distance of my successor route. So in the case of R3, here's what that means. R3's reported distance of 11,000, it must be less than, not equal to, it must be less than my feasible distance going through my preferred path, which we said was 16,000. The question is 11,000 less than 16,000? Yes, it is. And because the answer is yes, then we will say, okay, we'll allow R3 to be a successor route. It's going to be, I'm sorry, not a successor route. It's going to be a feasible successor route. But when we take a look at R4 and we say, is its reported distance of 18,000, is it less than my feasible distance of 16,000? No, it's greater than. So even though we can look at this and say, oh yeah, that's a loop-free path, let's use that. If the other two fail, I mean, it's slow, but it'll get us there. No, the router says, I don't trust that. I'm not going to make that a feasible successor. It fails. That means we're not going to fail over to it immediately. It doesn't mean we'll never fail over to it, though. Something we get into in the NARCI class is we talk about something called the query process. So we go into R1 goes into an active state and it sends some queries, and there's a bunch of stuff going on there. But I just want you to know that R4 will eventually be used, but maybe not in 2 or 3 seconds. But that's the way that EIGRP is going to make its path selection decision. But how did we come up with those numbers? Those are some big numbers, weren't they? We had like 16,000 and 5,000. What's up with those really super big numbers? Well, EIGRP has a very convoluted formula for calculating the metric, and it's based on 5 different parameters. And notice I'm just showing you the first letter because I want you to write down a memory aid. And this memory aid is going to remind us of the 5 things that can go into EIGRP path or metric calculation. And I hesitate a little bit on that because we're going to see that one really doesn't play into the formula. But let's go through them. I want you to think of the acrostic, if you want to write it down. Big dogs really like me. Little dogs do too, but big dogs really like me. Write that one down. The B in big reminds me of the B in bandwidth. Think of the B in big reminding you of the B in bandwidth, and the D in dog reminding you of the D in delay, and the R in really reminding you of the R in reliability, and the L in like reminding you of the L in load, and the M in me reminding you of the M in MTU. So the bandwidth, the way that's calculated, you take the number 10 million, 10 to the 7th power, and you divide it by, in kilobits per second, the link speed of a particular interface, and that's the bandwidth. And we don't, if I have to go through 3 routers to get to my destination network, I don't say, well, let's add up the bandwidth here and here and here. No, we look at, we say, who is the weakest link? Do you remember the old NBC TV show from many years ago called The Weakest Link? And they would say, you are the weakest link. Well, the bandwidth is the weakest link. Whatever the slowest link is from us to that destination network, that's the bandwidth number we use. Now, delay is cumulative. Every time we exit a router interface, we add a little bit of delay. So if I got to go have 3 router interfaces, it's a little bit, and it adds, and we're looking at the total delay. Reliability is a fraction. It shows how many packets are getting through versus the number of packets that we sent. It's a ratio over 255, so 100% reliability would be a value of 255. Load is how busy the link is right now. It's also a fraction. It's a number over 255. We're saturated if we're at 255, but we're minimally loaded if we're only a 1. And those 4 values, they plug into that metric formula that you see on screen. Yeah, soak that one in if you would. That's a doozy. But you'll notice that MTU is conspicuously missing. We say it's part of this, but it's not really part of the formula. It's there as a tiebreaker. So if you've got 2 different ways of getting somewhere and you say, well, they got the same metric, look at the MTU. Because if you haven't configured variance to load balance across unequal cost paths, you're trying to find the best path. So you're going to go with the one that has the highest MTU. So I knew what you know now when I was at my technical interview at Disney. I mentioned I missed the spanning tree question I told you about yesterday. I missed this question also. It's a wonder I got the job. But I missed this question. They said, because they ran EIGRP, they said, by default, what does EIGRP use to calculate its metric? That was their question. And I thought, I got this. I remember the acrostic. I knew off the top of my head, big dogs really like me. So I stood up there and I said, bandwidth, delay, reliability, load, MTU. And they said, no. Really? They said, that's not what it uses by default. What I was not considering is in this formula, there are these different, they're called K values. And I have those listed for you on screen. There's 5 of them here. These K values are are a way for us to make one parameter have more or less influence on the overall metric. If I think reliability is, well, let's say if I think bandwidth is more important, I could inflate my K2 value to something really, really high, as an example. But with these default values, if we do some plugging and chugging, you're going to see that it all boils down to just bandwidth and delay. Now, I don't want to get too much in the math here. That's for the NRC discussion, but somebody's going to look at that and say, K5 is 0. That last K5, 0 divided by K4 plus your lot, everything is going to be 0. If K5 is 0, everything is 0 according to this formula. There's one exception to the formula, and that exception is if K5 equals 0, then K5 divided by R2 plus reliability, that quantity, it's a 1. So it's not a perfect formula, and it is a confusing one. But that's the way that EIGRP makes its selection decisions. Now, just a few words about BGP before we take your questions, and that is just at a high level. We talked a little bit about this before, but BGP is going to be our exterior gateway protocol of choice. In fact, it's pretty much our only choice these days. Oh, pop quiz for you in the notes or in the chat. Does anybody know, besides BGP, can anybody tell me another exterior gateway protocol? Is there another EGP other than BGP? Or I'll say today, the answer is no, but there used to be. Can somebody tell me an older, now out of date, exterior gateway protocol? Go ahead and chat it in if you happen to know that. Wow, Terrence has it. Coming in really quick. Awesome job. Yeah, there was actually, and Guest 5104 has it as well. Yeah, Terrence, great job. Yeah, it was actually called EGP. There was an EGP that was named EGP. We don't use that anymore. It's now just BGP. But unlike sending out those multicasts to say, hey, let's discover our neighbors, no. With BGP, we statically configure our neighbor's IP address. And we actually set up a TCP session, kind of like we set up this ongoing conversation, this reliable communication path. And we advertise subnet mask information as well. In other words, the address and its length. The length being the number of bits in the network address. And instead of having something simple like, here's the formula for metric, or here's the formula for cost, you thought EIGRP was confusing about how to calculate the best path? You should take a look at BGP. It uses something called path attributes. These path attributes, let's just a few of them. We have weight, local preference, origin code. There is something called the metric, which is it's called the multi-exit discriminator. We've got the autonomous system path. There's grand total. It depends on the literature you read, but it can be as many as 13 different things we look at. If you're just curious as to what those are, I'll recommend that you go watch that BGP video I mentioned to you before. It's on my YouTube channel. Search for Kevin Wallace BGP. It's the one where I'm looking at an orange, but it's complicated. And this did not really fall under the category neatly of a distance vector routing protocol, nor did it fall under the category of a linked state routing protocol, because it was a path vector routing protocol. It's not linked state because it doesn't have a map of the network. It doesn't know how. This is the protocol that runs the internet, by the way. It does not know about, let's see, I think, what are we up to now? I think we just exceeded 800,000 routes on the public internet that these routers know. If they have the entire internet routing table, they're storing over 800,000 routes, and they're going to use BGP to make those routing decisions. So it's not going to have a map of how all those networks are interconnected, but it does know the next hop, so it's a vector. But what's up with the path? Well, I think I mentioned this in a previous session. As it goes through different autonomous systems, it's going to give you a list. It's going to show you in the output, here are the autonomous systems that we have transited. Those are the autonomous systems that we have crossed. So that's the reason it's called a path vector routing protocol. Now go ahead and start typing in your questions if you would. And I know Charles at the top of the hour, he always emails me a series of questions as well that you guys have been asking. So I'll take a look at that. But I'll take a look at the chat here and see if I see any questions coming in. Put question marks in front of them if you would. Oh, while you're doing that, I did want to bring up again the CCNA masterclass that we have coming up next week, we talked, and I'll just go through this briefly because we talked about it in depth yesterday, but some people might be new today. I was telling you, for your career, based on my 3+ decades of experience, there are three levels, or there are three elements that lead to really mastering your IT career. One is immersion, where you go into a class and day after day after day, you focus. You focus on this topic. You've got a taste of immersion this week. If you've been with us throughout, you've got a taste of what immersion's like. If you come join us for the CCNA Masterclass next week, you're going to get 4 days of immersion. And depending on which tier you sign up for, you might be joining us for a 5th day as well. But you don't want to just have that one powerful immersion and then let it evaporate over time. You need continuous learning, and you need some coaching, an external perspective. A coach is not necessarily better than you. They just have another perspective. They have some strategies that they can share with you. So that is what we offer here at KW Train. And if you'd like to take the first step of immersion, we've got coming up next week, and that all leads to your career mastery. But coming up next week, we're having a CCNA Masterclass. It's the last one we're doing this year. And this time, for the first time ever, we're doing 3 different tiers that you can sign up with. And the basic, because I know budget is a real thing for many people. Your company's not paying for it. I mean, things are tight. I get it. So we made the least expensive masterclass by far than we've ever done. You will not find anybody else doing this. And we call it the general admission. And until sometime tomorrow, the price, it goes up at the end of tomorrow. But if you buy today, $97. $97, and for that, you get to attend this 4-day virtual live class, much like we've been doing this week. It's going to be 4 days. We cover every single topic on the CCNA Blueprint. I'm going to be teaching you, and honestly, not doing this from an ego standpoint at all. I'm just saying that a double CCA teaching you live an entire CCNA class, it doesn't happen. It sure doesn't happen for $97. That's crazy. I don't know of that ever happening. We've never done it. And in addition to that, you get access to like-minded professionals. You get to be a member of this private tribe community that goes on after the class is over. So you get to help one another. And you get that collective IQ, and you get a replay of this week's course. I told everybody that, the CCNA Foundations class, we're taking it down tomorrow. But anybody that signs up for the class, you'll get it free. In fact, I've already been putting those of you that have already bought, you see it. It's in your membership area, and you see it right now. But you'll get these replays. And something that we're trying to do, I know with all the COVID-19, the charity that we primarily support here at KW Train feeds school children that oftentimes don't have food on the weekends. And we're still going to make a private donation. But I thought it'd be great, especially during this time, for this community to help as well. So on your behalf, when you buy the general admission, we're going to donate 5 meals to that local food bank. Most people, though, they're going to be going for the executive admission. What that gives you, it gives you everything that you get with the general admission for $297. Again, that price goes up tomorrow, but you get everything in the general admission plus. After each of our classes next week, Monday through Thursday, after you get out of this session, you're going to jump into a Zoom call where it's going to be us, and we're going to be able to chat back and forth, and we'll spend another 30, 45 minutes, whatever it takes, to answer your questions and maybe get some feedback from other people where we actually get to see each other face to face. I love to see your faces. Something else we're going to throw in is we're going to give you a replay of next week's masterclass. Now, if you want to go with the general admission, you can show up every day live, take notes. Awesome. But if you want replays to go back and revisit, the executive admission gives you replays of next week's class. And I know you want to practice, so we have created a very thorough practice exam. You can take it online, you get graded, you can download a PDF. We're also throwing in a course, because there's a lot of wireless content on the new CCNA. We created a wireless crash course, and you get that for free. We'll throw that in. And we also you want hands-on experience. So we give you our Packet Tracer course that shows you how to download Packet Tracer for free. We give you video walkthroughs and Packet Tracer files to get a lot of hands-on experience. And we'll donate 20 meals to the local food bank. And this price, even though this is nearly $1,000 value, if we were to buy it individually from our site, it's less than $300. That's a crazy low price for this that you get to keep forever. You get to keep this content forever. But if you're not just going after the CCNA, you know that your future is in CCNP. It's just a matter of time. Now's the time. It's not going to change anytime. The exams just came out this year, so it's not going to change anytime soon. We invite a few of you for the Diamond admission. Now, we said yesterday that the first 10, they're going to be part of this. They're going to be part of a mastermind that we're going to be doing. That has filled up, but don't worry, I've got something else for you. But that's filled up. The mastermind is full. But for the Diamond admission, you're going to get it for $797. Now, obviously, that's not for everybody. But if you know you're going to be going and getting your NP Enterprise, this is the one you want to go for. Not only do you get everything in the executive admission, we give you our Encore video training series that we developed over many months. It came out earlier this year. And we also give you our Anarsi video training series that we just released earlier this month. So you'll get both of our complete video courses, and wow, that's like a $800 value right there. Plus you're getting all this other content. And because we want you to have not just the ongoing training in that little Venn diagram that I gave you, we want you to have coaching. So we're going to give you 6 months free membership in our coaching program, in our ongoing training program, where we go live once a month. We can talk about whatever you want to talk about. I do some training every month, but we can help one another. It's a really tight community that we've been keeping to under 100 people, but we've got some openings now. And 6 months free. After that, it's $44 a month. It's not going to automatically enroll you. We'll contact you after the 6 months and we'll ask, do you want to continue? We're not trying to trap you into something where you're going to get charged if you don't want to. And the first 10 people, being in our first ever mastermind, that filled up quicker than I thought it would, honestly. But and we're donating 50 meals in your name. But I wanted to do something for the people. And by the way, that's over $2,000 of value that you're getting for $797 until the price goes up tomorrow. But I wanted to do something else since the mastermind's full. I thought, you know what? For people that are really going to be all in on this, and by that I mean you're going in at the executive or you're going in at the Diamond edition, I want to give everybody just a crazy bonus. Now, those of you that already bought, you know what I'm talking about, because less than an hour before class, you probably started getting these emails saying you've been granted this course, and you've been I gave everybody that bought yesterday, I gave everybody 5 additional courses. And here's what the deal is. I've been so excited to share this with you today. By the way, here are the links that you'll go to purchase, and I'll put these right back up. But I've been so excited to share this. I left one of our core values is generosity here at KW Train. So here's what we're going to do. If you make your purchase before the class is over today, here in, I don't know, a couple hours or so, if you make your purchase before class is over today, I've already added this to the courses that you purchase, and you purchase specifically the executive or Diamond, not general, but executive or Diamond, you'll get these courses. We'll give you the BGP course that we came out with earlier this year. My good friend in CCIE, Anthony Sequer, created that especially for us at KW Train. Another class that we had created especially for us, for my friend Michael Shannon, because cloud is a big deal, especially on this new enterprise track. We'll give you a cloud computing course. IP subnetting, as you saw from yesterday, it's going to be one of the more challenging topics. So we give you a course dedicated to subnetting. It includes a PDF with I think it has like 12 practice exercises, detailed explanations that you can print out. Spanning tree that we touched on yesterday. We did a deep dive course and recorded it. It's called the Spanning Tree Protocol Crash Course. We're going to give you that for free. And OSPF, that's another that is the only protocol on the CCNA exam, but you need to know about that for your next step and your next step. So we're going to give you our deep dive OSPF crash course. If you were to buy these individually, BGP is like $100 and the others I think are like $49 each. That's like $300 extra. And those of you that have already bought, go check it out. You have them right now in your members area. And right after class today, because you think, oh, Kevin's trying to create urgency for me. This is a marketing thing. I am trying to create urgency because here's what I've seen happen, and it kills me. So many people have good intent. Oh, yeah, I'll do it tomorrow. And the reason I know this is not my guess. I know this because we've had sales in the past. Okay, it expires at midnight. I cannot tell you how many people like contact me the day after and said, "Oh, sorry, I missed the sale. I really meant to do it. Can I still have the discount?" Sorry, the discount's over. But I've seen the procrastination really come back to hurt you. Yes, I want to create some urgency because I want it for your best interest. I want you to take action right now. I want you to buy before the class is over. And if you do, you're going to get unprecedented. We've never done this combination before. You're going to get those 5 free courses. Now, I'll put this up on screen. Those are the links. So now's the time to act. If you're going after CCNA and you want to join us next week for a deep dive training, it's going to be the best CCA training I've ever done. I've got some cool things planned. And if you're going to be going further, you know what to do. Diamond Admission. Let's take your questions right now, though. Let's see here. And actually, let me take a quick look at the questions Charles emailed to me. Then we'll check out your questions. We'll see. Well, we'll just see how many we get. Let's see. Savan, or Sevan, Savan, pardon me if I mispronounce that. Is there any software or hardware limitation for the database size for the link state database? Not with our modern routers. I've not heard. I mean, the recommendation was 50 25 years ago. I have not heard a recommendation since then. Disney is the largest single site employer in North America. Yeah, I don't think you're going to run into a limitation like that. Let's see. Larry says, can an ABR touch the more than 2 networks? Oh, great question. Yes, an ABR has at least 2 interfaces in more than one area. I worked really hard on that definition, which would account for what you're asking. Yeah, we could be attached to multiple areas, and we're going to have a database for each area. Oh, here's another fun term for your notes. If let's say we've got a router and it's attached to an OSPF area, let's say area 0, and it's attached to an EIGRP autonomous system. We had a couple of companies merge. One was running OSPF, one was running EIGRP. What do we do then? Well, that router is, here's the term for your notes, that router is called an ASBR, an Autonomous System Boundary Router. An Autonomous System Boundary Router. That's going to interconnect a couple of autonomous systems. But yeah, the quick answer was yes. And let's see, let's take a look at 1 or 2 questions here. Just doing a quick scroll through here. Let's see. Somebody says, if they're both lower, do we go with the lowest of them? I'm not sure if you're referring to MTU. That was Jen that asked that. Jen, if you would maybe clarify that a little bit. I'm sorry I missed that. Let's see. Patrice is saying, Kevin, will a NARCI masterclass be available on Udemy like Encore? No, we don't. Right now, we don't have any. We don't have any training on Udemy. We were just kind of doing a little test. It's not for us. No, you cannot go to Encore, or you cannot buy any of our stuff on Udemy. But we are going to be having an NRC masterclass. Charles is going to be leading that up. I think it's in December of this year. I'm going to be doing an Encore masterclass live. I think that's in, don't quote me on this, it's either October or November, but those are coming up. All right. Yeah, that's a good chunk of questions for the day. Let's go ahead and take our break. I'll tell you what I'll do. I'll leave these links up. And remember, after class, those 5 bonus courses, they go away. So hopefully you will take advantage of that. And I'm going to put on some music, and I'm going to set a timer. Set timer for 10 minutes. All right. We'll see you back in 10 minutes, everyone.
Okay, 10 minutes and counting.
welcome back from the break, everybody, and thanks to everybody that took advantage of that offer that's expiring at the end of our show today. Our next big topic that we're getting into is not on the CCNA exam, but remember the purpose of this foundations course. It's to give you sort of a sampler platter, if you will, of all things networking. And one of my personal favorite topics in the world of networking, you can go down this track in the Cisco curriculum after you get your CCNA, or actually even if you don't, you can go down the Unified Communications track. In fact, the next course that I'm going to be developing starting next month is on Unified Communications. So let's get into some of the basics. It kind of boils down to the replacement of a traditional phone system. For years, companies, they would buy their own privately owned phone switch that was called a PBX, a private branch exchange. And that PBX would have a certain number of lines going back to your local telephone company, back to the central office. Because, I mean, think about it. When I worked at the university, I think we had about 6,000 phones on campus, but we only had about 200 phone lines on campus. I mean, it would be prohibitively expensive to pay 6,000 phone bills every month to the telephone company with everybody having a line, but not everybody's going to be using the phone at the same time, so we can kind of just share this pool of resources, this pool of lines, and the PBX would do that for us. But then we used to have a separate network, so it would be a separate video network. Literally, I could go into a wiring closet and it would be, here would be the fiber for the video network, and here would be the fiber for the data network, and here would be the fiber for the voice network. But like they said in the Field of Dreams, if you build it, well, actually, they actually don't say if you build it, they will come. It's if you build it, he will come. But you get the idea. If you build a network reliable enough and fast enough, then we can start to have everything live on that same network, the voice and the video and the data. So we started to replace those or actually started to interconnect those PBXs using routers. What we could do is we could have the PBXs connected to routers, and the routers could go over the IP WAN. And then we started having the routers do a lot of the job themselves. You can get interfaces for your routers and literally plug analog phones into those routers. But let's talk about the magic of how does the spoken voice, as you hear words coming out of my mouth and going into this microphone, it's being digitized as it goes into my computer and then streamed out to you. How does that happen? Well, we have an analog waveform coming out of our mouth, and we want to convert it obviously to a digital waveform. So what we do is we take that analog waveform, and it's a lot like when you go to the movies. If you go to the movies and you're watching this, if you're watching the movie up on screen, you're not seeing smooth motion. Now, it might look like smooth motion, but really you're seeing typically 24 frames projected in rapid succession every second. And there are so many of them, it looks like smooth motion. Well, with voice, we take metaphorically snapshots of the analog waveform coming out of our mouth. In other words, we measure the amplitude, and with all these little measurements, we can digitize those. We can assign numbers to those, send them across the network, and at the other end, we play a game of connect the dots, and we reproduce a waveform by connecting all those samples. But if you don't take enough dots, notice I'm showing you here on screen the original signal. If I don't take enough dots, or I don't take enough samples, and we interconnect those, that's going to create a totally different waveform. It's going to sound nothing like the original waveform. That's called an aliased signal. And we could take more than enough. That would actually improve the voice quality a little bit. But if you take a whole bunch of samples, that's going to require a whole bunch of bandwidth. So what's the balance? What's the happy medium there? Well, the answer actually came from an engineer that worked for Bell Labs back in the 1920s. His name was Harry Nyquist. And he came up with a theorem that there's a big history behind that. I won't get into all of it, but the bottom line from the Nyquist theorem is if you want to accurately reproduce a waveform, the minimum number of samples that you need to take equals twice the highest frequency that you're sampling. So with the human ear typically hears about 20 hertz at the low end and about 20,000 hertz at the high. Well, young human ears typically hear about 20,000 hertz at the high end. I listen to a lot of extremely loud music when I was a teenager, so I might not be hitting that 20,000 hertz like some of you may be. But the point is, if we wanted to accurately reproduce 20,000 hertz, we would have to take at least 40,000 samples per second. That's a lot of samples. But if we look at human voice, that's what we're trying to send over our network. If we're trying to look at or trying to reproduce human voice, if we take 4,000 hertz and look below that, over 90% of voice happens under 4,000 hertz. So we're getting the vast majority. If we just say 4,000, that's our highest frequency. So how many samples do we take? Well, 4,000 times 2, that's 8,000 samples that we need to be taking every second. And we go through a couple of processes. The first process is called PAM, P-A-M, pulse amplitude modulation. We're measuring this amplitude, and then we're taking that amplitude and representing it using pulse amplitude modulation. We represent everything as a single frequency at different amplitudes. And we kind of put those on a graph like this, and we say, hey, what number are you nearest? And if we're nearest to the number 1, we'll assign a digital number 1 to it. If we're nearest to number 2, we'll assign a 2, and so on. But you'll notice none of these that I have on screen are perfect. There's a little bit of error. None of them exactly hit right on the number. What is going to be the result of that? Well, that's going to lead to something called quantization noise or hiss in the background when you're listening to something. Now, obviously, we can make this more accurate by having more discrete measurements that we could assign. But the more measurements that are possible, because there are an infinite number of measurements that we could use, again, what's the happy balance? We want to be able to represent any sample with just 8 bits. With just 8 bits. So, what does that look like? If we just leave it on a linear scale, you're going to get a lot of that quantization noise. But we can make the most out of our 8 bits by using a logarithmic scale. Remember in high school, did you have the log paper like I did in high school, where it was like 10 base 10 logs, and you had the spaces that are represented in ones and then tens and hundreds and so on? That's what we use when we're digitizing voice. We use a logarithmic scale like you see on screen, where we're taking more accurate samples at the lower volumes. That's good for 2 reasons. One reason that that's good is most samples occur at the lower volumes, so we're being more accurate for more of our samples. And another reason that it's better to be more accurate at the low volumes is at the high volumes, they're so loud they tend to drown out all of the background noise anyway. So we use a logarithmic scale, and notice we divide things into segments, and then those segments are divided into individual steps within those segments. And it could be positive or negative too. It could be above the line, it could be below the line. So what we do is represent a sample with 8 bits. One says, is it above or is it below the line? What's the polarity? Then we use 3 bits to say what's the segment. We use 4 bits to say what is the step within that segment. Grand total, we've got 8 bits. Mr. Nyquist said we should take 8,000 samples per second. What is 8 times 8,000? 64,000 bits per second, 64K. Does that one ring a bell? That's the uncompressed bandwidth required for voice. And the way we encode voice on Cisco IP phones, we can use a variety of codecs, which are short for coder decoders. And a codec is going to use an algorithm to represent voice digitally. And if we don't do any compression, if we're trying to be lossless, and we use the entire 64K, we might be using the G.711 codec, and I won't read through them, but there are other codecs that will give you more bandwidth savings at varying levels of quality. That's a topic for a collaboration course. But I wanted you to be aware of that actually came up in a class I had not too long ago, and I thought, that's a great question. I should really expand on that a little bit. So that's how it happens. That's how the spoken voice becomes ones and zeros. And there are several different pieces and parts that go into a Cisco unified collaboration system. And I'm not going to go through all of them. Let me just give you the basics. In the Cisco world, we have Cisco IP phones. They have an Ethernet connection in the back of them. So they're going to connect into your Ethernet switch like most things do. A lot of your Ethernet switches do power over Ethernet. They'll actually power up the phone from the switch. It's going to be able to send power over the same cable that's sending the Ethernet signals. So that can power up the phone. And the phone is going to register with sort of the PBX replacement. And it's called the Cisco Unified Communications Manager. Think of that as, well, think of that as the PBX replacement. It's going to have all the dial plans. You dial a number anywhere in the world, it's going to know what to do with that. If it's in the neighboring office, it'll send it to the neighboring office. If it's around the world somewhere, it will go out to the PSTN, out to the public switch telephone network. And it's going to do that through a gateway, which is typically a Cisco router. And in our collaboration studies, we get into all that. I just wanted to give you a sense in this course. So don't think, oh, he didn't talk about this bullet or that bullet. No, I just want to give you a sense for what's going on here. And something that's sort of come on the scenes and become a big deal in the last 10 to 15 years, video. We're not just sending voice anymore, we're sending video. That's the reason they actually changed the name of the track. They no longer call it the voice track, they call it the collaboration track, because it's not just voice, it's video, it's instant messaging, it's presence information. If you use something like Cisco Jabber, it gives you all of those things. So we could have video calls between phones as an example. Now, when we think about video, there's a lot of confusion with some of the terms. So time to grab your pen again and take some notes. When I was talking about that movie, and I said we were watching 24 frames per second, we were, but let me see, I don't know if I have a light. I was hoping I had a flashlight in my desk. I'll use the flashlight on my phone. That'll work. So here's the flashlight on my phone. Let's say that the movie is going in front of the camera projector like this. Well, if it just constantly streams, it's going to be a big blur, isn't it? So what's going to happen? Well, a frame is going to come down and it's going to be projected, and then a shutter is going to block the light. While the light is blocked, that frame is going to move down, and then another frame is in front of the projector, and the shutter is going to come up. So that's why you see blinking a little bit of the time, because it's being blocked part of the time. But if you were to do that with 24 frames a second, that would be somewhat noticeable. It's like blink, 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 blink. But so what you do typically in a movie or on TV, you don't see, on TV it's usually 30 frames per second. Well, let's take TV for example. With TV it's 30 frames per second typically, but you don't see 30 frames, or you don't have 30 shutter up and downs per second. You might have 60 or 120 or 240. You see what happens, that celluloid comes down in front of the projector, the shutter comes up, the shutter goes back, leaving that same frame there. The shutter comes back up and comes back down, or the shutter comes up, then we advance and it comes back down. So we're actually seeing the same image twice, if you will. The shutter's coming up and coming down and blocking the same image. And that's so we don't notice a lot of flicker. The reason I'm describing all that is that's the refresh rate. If you're into gaming, or you look at you go to your Costco and you look at all the cool TVs and you look at the refresh rates, yeah, the higher refresh rates, the smoother the motion is going to look. And with some of our Cisco telepresence systems, we've got these big, massive screens, and it's kind of eerie. If you've ever had a conversation using Cisco telepresence with one of those big screens, the audio quality is just perfect. It's really gives you the feel of standing in front of someone or sitting in front of someone and talking with them. But that's the refresh rate. Now, when we paint the video on screen, one way of doing that is to use interlaced video. This is going to allow us to get a higher definition picture with less bandwidth. It's going to be like this. We're going to paint every line during one of those refresh rates, and then we paint the other line during the other refresh rate, and that's going to allow us to have high. You've heard of 1080p? 1080p is progressive. 1080i is interlaced. So interlaced still technically gives you 1080 rows, but it's not going to be as smooth. You're going to have a lot more blurring going on. So that's the difference between interlaced and progressive. And we know what a pixel is. A pixel is a little picture element, and I took a picture of the music icon on a couple of iPads I have. One is, let's see, where is it? Yeah, this is the iPad Pro that's got the Retina display, and then I had a really old iPad that did not have the Retina display. And if you zoom in, you can start to see the one on the left. It's a little bit more blurry. Now, aspect ratio, that's the ratio of the of your screen. Now, for years, traditional television sets, they were like a 3:4 aspect ratio. Well, that's radically changed now to like a 9 by our 16:9 ratio, where however many columns you have, that ratio is like 16 compared to the number of rows you have, and that ratio is 9. So, for example, 1080p TVs, you've got 1920 columns, you've got 1080 rows, and with 4K TV, that sort of doubles everything. You've got like 4,000 vertical columns instead of 1920 vertical columns. And the protocol that we oftentimes use in the voice over IP world, in the video over IP world rather, is H.264. That's a standard, and it's used for tons of video, for video editing and compression, and it's what's used by your Cisco IP phones and your Cisco routers much of the time. Now, I don't want to dwell. I pulled in a bunch of my collaboration slides to give you a sense of that, but certainly this is not a collaboration course. So I don't want to continually dwell on that. Actually, we were done with the collaboration. I thought, let's go on to the next module, but what do you know? We're done. I thought about that ahead of time. One of the big technologies that you're hearing a lot about these days is cloud. I mean, the cloud course, that's one of the free courses that we were giving away for people that purchase. And virtualization is another big one. Now, when you think of virtualization, a lot of people don't think of this, but it counts. This is a virtual IP address. Think of your computer wanting to get out to the internet. Well, when it wants to get out to the internet, it goes to a default gateway. Doesn't that default gateway sort of seem like a single point of failure? I mean, if the gateway goes down, you're not able to get out to the internet at that point. Yeah, it kind of does, doesn't it? So what we can do is use something called, for your notes, a first hop redundancy protocol, an FHRP, a first hop redundancy protocol. That's something I'd want you to know for your CCNA exam, a first hop redundancy protocol. And and we won't go into what they are in this class. Well, I'll tell you what, they're HSRP, VRRP, and GLBP. Those are the three that we talk about in your enterprise track studies. But what they do is they make more than one router available to get us off of our local subnet. So if the main router goes down, the other router steps up and it takes over for us, or it takes over for that first router that went down. Now, virtual servers, that's what I often think of when I think of virtualization. I remember when I worked back at the university I was telling you about, we had a server farm with these big racks of equipment. And what we did, we had different colleges within the university. We had like the College of Computer Science, the College of Business, the College of Nursing, and so on. We bought each college a big, massive Dell server. For that day and time, we packed it full of hard drive and RAM. And we said, all right, here's your server. You can do all of your college stuff on this server. You know what? It really didn't get utilized that much. We were lucky if a server got 2% utilization. It kind of seemed like we wasted a lot of money because we threw a lot of money at servers. We wanted to keep the colleges isolated. We didn't want College of Business saying, hey, the College of Nursing is taking up all of our space. No, we wanted to keep them isolated, but there was a lot of wasted resources. Well, we can get away from that these days by virtualizing servers. We can have what's called a hypervisor that we can install on a computer, and that hypervisor allows us to install an operating system on top of it. And that way, for example, we could have a server that runs VMware ESXi. And on ESXi, I could install an Oracle server. I could install a Linux server. I could install a Microsoft Windows server. There are virtual servers. They're isolated from one another, but they're on the same physical platform. Now, I'm curious. Can you tell me in the chat, if you would, what hypervisor or hypervisors are you using? Now, the one I just told you about, that's called a bare metal or a Type 1 hypervisor. It runs directly on the machine. But I'm running Mac OS right now. I've got VMware Fusion installed on my Mac, so I can run virtual machines on my Mac. That's sitting on top of an existing operating system. Let's see. Hyper-V. Yep, I forgot to mention that one. KVM. Lots of VMware. Oh, VMware Workstation for Microsoft Windows. Hamid saying ESX5. Jen saying VMware. Oh, Jen, I noticed during the break you did respond to my EIGRP question, so just really quick on that. Jen was asking if your neighbors are giving you the same reported distance. What do you do then? If they give you the same reported distance and your distance to them are the same, then you're equal you have equal cost, and you will do load balancing by default. But we got ESXi, KVM, works. Yeah, awesome. So I'm glad this is not a new concept to you. So you know how good it is. And within your virtual machine, here's what I've done for the collaboration training that I do. I get one. I think I've got these two HP rack mountable servers down in my basement, and they're loaded up with the hard drive and they're loaded up with RAM. And I install virtual servers on those. I install a communications manager server like we talked about. I can install a voicemail server. I can install a presence server. And not just servers, I install virtual routers. Yeah, Cisco has something called the CSR1000V, the Cloud Services Router. That's a router that you can install on the computer. It's amazing. And in fact, Cisco, I think they still make a free one available. If you want to check it out, go to my YouTube and search for Kevin Wallace CSR for Cloud Services Router, and I'll walk you through how to get it installed. But we can install more than just regular servers is my point. And each of those devices that we install, they've got their own virtual network interface card. And what I've also done is I've set up more than one virtual switch. So I can have a virtual router connect to a virtual switch, connect to another virtual router, connect to some physical servers, and then finally we can go out through the physical NIC. So I've got a fairly robust topology of like 2 routers and 3 switches and 6 servers all running within the confines of that one physical server. And virtualization doesn't even have to be at your company locally or in my basement. We could virtualize these servers out on the internet with cloud service providers. Like, Amazon AWS is the first one that comes to mind. Google, Microsoft Azure, and Google Cloud Services, they all have their own. But it doesn't even have to be done on our resources. And as I was pointing out before, it's not just traditional servers that we can virtualize. You can virtualize the routers like a CSR1000V. You can virtualize Cisco Nexus switches. You can virtualize Cisco's Adaptive Security Appliance Firewall. You can virtualize a load balancer. Just amazing the number of things that you can virtualize these days. And we can do that in the cloud. So used to, when I would want to set up a collaboration lab, I'm getting on eBay and I'm buying lots of switches and routers and all these different servers. And now I can pretty much set up the entire topology except for the phones. I can use Jabber for that, I suppose. I can set up pretty much the entire topology on 1 or 2 physical servers. It's amazing. And the cloud, as we start to move those virtualized devices to the cloud starts to play a bigger and bigger role in today's network. And it's okay these days to use the cloud, but years ago, the speed would have been so low relatively going to the cloud, it would have been prohibitively slow. We couldn't do effective business if we were trying to pull resources down from the cloud. But these days, with gig and 10 gig connections out to the internet, yeah, it's fine that we're using the cloud or Metro Ethernet. But if we're going over the internet, that seems a little unsecure, doesn't it? Or unsecure, yeah. I get insecure and unsecure mixed up. Insecure happens to a person. Unsecure is what happens to a network. But it's going to be a little unsecure. So how do we make the internet secure? Well, we've talked about it. We could use a VPN. That's where we can set up, like, remember the GRE over IPsec tunnel. That would do it for us. Or we could have a private connection. We talked about MPLS. We talked about Metro Ethernet. Those would be alternate options. And there are so many different cloud providers. We may want to change providers from time to time. Let's say we've got cloud providers 1, 2, and 3. And for a while, we were getting the best rates from provider 2. But now we want to switch over and we want to start using provider 1. That's a lot of work to do, by the way. But what a lot of companies or some companies are starting to do now, this is now growing in popularity, instead of connecting to a specific cloud provider, you connect to a company called an inter-cloud exchange. It's their responsibility to connect to the different providers. So if you say, I want to go from Azure to AWS, They do it. You just have your peering relationship with them, and they do the heavy lifting of getting you connected to that final destination. So that's a quick look at cloud and virtualization technologies. Next up is a bigger topic. We'll be on this one for a while. It's network security. So I'm just going to take a look at my chat boxes right here. Any questions really on anything we've talked about up till this point? I know this is the last day of class, so let's don't hold back any questions. Preface it with question marks because, as you can see, and I'm looking at two different chat boxes, so there are a lot of questions out there. Let's see here. Somebody asking if I use Cisco phones in my house. I used to have them set up when I taught collaboration more. Not currently. I don't. Just for lab environments. That'd be cool though. Let's see. Please explain how. Let's see. Okay, a couple of good questions from Edgar. Says, can you please explain how the VNIC works internal? Sure. The VNIC, that's the virtual network. A virtual network interface card. When you install a server, like on VMware ESXi, it's going to ask you what your virtual network interface card is going to connect to. And if you've got a physical interface in your switch or in your server, you can say, all right, I want to connect it to, it's called a port group. You're going to connect it to this port group. And that port group contains your physical network interface card. But you could create your own virtual switch and put the ports in that virtual switch in your own port group. So you're setting up your server and you say, I want to connect this virtual network interface card to this port group to use this internal switch because maybe I want to connect to a router that's inside of my physical piece of hardware. So you're not limited to a single VNIC per server. In fact, when I'm setting up a virtual router, for example, I'm setting up one of those CSR 1000Vs. I may want it to have 4 interfaces to connect out to 4 different networks. You can do that. You can create. You can go in as you're setting up the virtual machine that the router is going to run on. You can just add virtual NICs and just tell them what switch to connect to or what port group to connect to. That port group might lead you outside of your server. It might be going to the physical NIC, or it might be going to a virtual switch that you have created. Let's see, we had a great question about OSPF. Can we only have OSPF version 3, which will also do OSPF version 2 at the same time? In other words, can we have one OSPF to rule them all? That is a very insightful question. I wish I knew your name. Yeah, when you sign in, if it's possible for you to put your first name in there, I'd love to call you by name because Guest 5104 has a great question. I just don't know their name. But that's a great question. Let's talk about that, and then we'll jump into network security. There are 2 ways of setting up OSPF version 3. One of them is the traditional approach. And with the traditional approach, it's only going to be routing IP version 6. So if you want to route both, you're going to have OSPF version 2 for your IPv4 traffic, and you're going to have OSPF version 3 for your IPv6 traffic. However, to your question, there is another type, or there is another way to configure OSPF. It even uses different commands. It's called, different show commands to verify it. It's the address families approach to OSPF. What you do is you create what's called a virtual instance. And under this OSPF virtual instance, you can have an instance for OSPF version 2 and an instance for OSPF version 3. Well, I shouldn't say OSPF versions. You can have an instance for IPv4 and an instance for IPv6. So this one hierarchical structure contains both your IPv4 and your IPv6 configuration. So the quick answer to your question is no with traditional OSPF version 3, yes with the address families configuration for OSPF version 3. Hope that was helpful. Well, let's talk about network security because that is a huge deal. We're hearing more and more about it on the news all the time. So let's begin by talking about some common network attacks that are out there. And then we'll, after we get depressed about talking about all the ways that we could be attacked, we'll talk about some mitigation strategies, how to make things a little bit better for us. But One of the biggest attacks that we hear about is called a DOS, a denial of service attack. This is where a malicious user will they'll just flood a victim's system with so much traffic that that system isn't able to do it's not able to do what it needs to do. We overwhelm its processor. We overwhelm its network link, as an example. Some different ways we can do that. One type is called a reflective attack. And here, the attacker on the left-hand side, on that topology, they're doing what's called spoofing their IP address. They're pretending to be the IP address of the victim. The victim that they want to attack has an IP address of 10.2.2.2. So what they're doing a ping, and they could do them not just a regular ping. We could say the timeout is almost nothing, and we could set the ping packet size very, very large. So we could have some aggressive pings going on. And notice we're telling an entire subnet. Notice we're sending this to 172.16.255.255. That's the directed broadcast address for a Class B network, which could, I don't think it would, but it could contain like over 60,000 computers. And those thousands of computers could simultaneously send their ping responses to this poor victim that had nothing to do with anything. They were just told that the packets were coming from 10.2.2.2 when really the attacker just said they were coming from there. Now, DNS, we talked about DNS the other day. It pretty large. It can have really large databases. Remember, we had those TXT records. There's a lot of information that the service records that told us who is responsible for that DNS server. We could pull a lot of information down, and we could flood a victim system with too many DNS replies. So that's something else we can do. It's called an amplified attack, where we pretend to be the victim and we ask for just a ton of DNS information from one or more DNS servers, which flood our victim system with all that DNS traffic. One that you hear a lot about, though, is the DDoS, the distributed denial of service attack. This is a coordinated attack that happens over time. Somehow the attacker over time is going to infect computers potentially around the world with software that lets the attacker bring them to life and trigger them to attack the victim system. Not making this up, those computers that get infected maybe via malware, they download something that looks like a game, or they go to some sketchy website and they get infected and they don't really know it for a while. Those computers are called zombies. They're literally called zombies. And the attacker summon the rise of the zombies, and the zombies rise up and they simultaneously attack our victim system. And what makes this so destructive is that over time, we're not just telling everybody on a subnet to attack our victim. We're telling potentially tens of thousands of computers from around the world to launch a sustained attack on our victim system. That can be very, very destructive. And one of the biggest ways that security compromises happen come down to social engineering. That's where somebody convinces maybe somebody in your company to give them information that they should not have. In fact, I want to bring something up and show it to you real quick. Let me give you a book recommendation if you enjoy books. Let's see. Let me bring this up on Amazon. Here is my favorite book on this kind of thing. It's called Ghost in the Wires by Kevin Mitnick. I think I've got about 3 of his books, but this is my favorite. It's let's see, there it is, Ghost in the Wires. That is a sort of, he just tells the story of exploit after exploit, ways that he hacked into systems that he shouldn't have been able to hack into. And what made me think to pull that up was a tremendous percentage of the attacks he was able to pull off was due to social engineering. He talked his way into like a courthouse room pretending to be some official, and he got in the back room where they had blank birth certificates, and he like stole a stack of blank birth certificates, and he made false identities. And Yeah, he did some crazy stuff. It's a really really good read. I've got it on audio and I've listened to it like 2 or 3 times. Highly recommend that one. Again, Ghost in the Wires by Kevin Mitnick. That's social engineering. An insider threat is what a lot of people overlook. They know that there are bad actors out on the internet that could be attacking them. What many administrators don't think about are the disgruntled employees within the company that might be doing bad things. They didn't get the raise they were expecting. Somebody got promoted above them, so they might have a beef with the company. So they might launch a threat from inside. So you want to really control what every person is allowed to do. Now, some people that might be coders within the company, they could plant what is called a logic bomb. And this goes off if a certain condition is met. For example, you've got an employee that wants to make sure if this company ever fires me, I'm going to bring them down. So what they do is they write code that will periodically go out and query the human resources database to see if their name or social security number is still in the database. If it's not, the conclusion is they've been fired. And if that condition is met, then this very malicious code launches, which can just start deleting tons of stuff. So very, very potentially destructive. Something else we might have is a rogue access point where somebody brings in an access point they bought down at one of the big box stores. They find an empty Ethernet jack and they plug it in. And they set up the wireless access point so that they can get to it. In fact, they might even hide the network name. They might hide the SSID so nobody else sees it. And that lets them have a way from some distance off to get into the network. Or, similar to that, you might have what's called an evil twin. This is still where you have an access point, but it looks like part of the corporate network. This access point has the same network name. It has the same SSID. For example, this used to be a big problem when smartphones were just, when the iPhone started coming out back in around 2007, and you were getting smartphones on wireless connections. If you got your phone from AT&T, most of the AT&T stores, they had their own internal wireless network that you could get onto without any password. And it was just, I forget, it was like called AT&T or something like that. And yeah, once you got on it and you told it to always reconnect to that network, somebody in a neighboring apartment, they could have their wireless access point set up advertising the network of AT&T, so your computer sees that or your smartphone sees that and says, a friend, and it logs onto that, and suddenly all your traffic is going through them. They're capturing it and then sending it to the internet. They don't want you to know that something's up, but that's what an evil twin can do. A lot of our software today, though, it will detect that. Good news, and it will protect us from that kind of activity. It will tell us that we have a rogue access point. Something else people do to try to find unsecured wireless access points is they do what is called war driving. Do you remember the old movie War Games, 1982? Matthew Broderick, Ali Sheedy. I was a big fan back in the day, but in that movie, if you saw it, Matthew Broderick, before he would go to high school, he had one of those old acoustical modems hooked to his computer, and he would set up a program to just call over and over and over again to numbers in his community. Just try this number, go to the next number. And when he would come back, there would be a printout of phone numbers that had answered with modem tone. So now he has a list of numbers that he can then try to hack into. He knows that there are modems on the other end of those phone numbers. Well, that was called war dialing. Well, war driving is where you're driving around a neighborhood or an industrial park, perhaps, and you're looking for unsecured wireless networks that you can attach to. And don't think that, nobody's going to do that. Perfect example. And by the way, this is not a bad thing. This is actually kind of a good thing. But I set up the wireless network at our church, and we've got, I think, like 9 wireless access points going around at the different place. Now, I didn't design the network to go outside of the church building, but some of the signal does leak out there, and it was unsecured so that anybody could just get on. Well, the local police department found out about that, and they needed to get on their laptops to do their regular reports. So they got in a habit of they would just pull into our parking lot, get on our Wi-Fi, and that's how they would do their reports. Now, I said that was not a bad thing because, hey, we were getting police protection during the night, so I'm all for that. I welcome them to do that. But in your company, do you welcome somebody to come up and and park in your parking lot and get on your corporate network, even if you have a guest network? Probably not. So you might want to be cautious about that. Another malicious malicious thing we need to be aware of is phishing. I see this all the time in my inbox. Phishing is oftentimes when you get an email and they claim that it's from. Oh, I got one the other day. This is one of the most recent ones I got. I got one from somebody that said they were from Apple, and they said that I need to reset my Apple password or my account was going to be deleted. I thought, wow, that's harsh. Come on, Tim Cook, what are you doing to me? And then I looked at it, I thought, the way it was written, just the wording that was used, even though it at first glance it kind of looked like it was from Apple, it was not from Apple. So yeah, I started to look at the email address that it came from, and they tried to make it look like it was from Apple. Not from Apple. But that was a way where I would click on a link. It would look like I was logging into my iCloud account, but in reality, I was providing information, my password, my username. I was providing that to this malicious user that would be capturing my information. One of the big ones we heard about on the news a few years back was an example of ransomware. Do you remember the ransomware called WannaCry? The WannaCry virus, because it made you want to cry. What it would do is, primarily on Microsoft Windows, you would get this big red screen, and it would say, if you don't pay this amount of money via Bitcoin to this Bitcoin address by this certain time, you're never going to be able to get to the data on your computer because we have encrypted the data on your computer. And the bad news is, they had encrypted your computer hard drive, and they literally held your data for ransom. If you didn't pay them via Bitcoin, then you didn't get your data back. And they would send you the key to unlock it if you would pay it, or so they said. There were plenty of people that paid the money and did not get unlocked. And when people started reporting this to law enforcement officials, it became so... It was kind of impossible to track them. It was very difficult to track them down or do anything about it. It was almost impossible to decrypt the hard drive that they had encrypted. The recommendation from law enforcement became, pay the ransom. If you want your data back, we got nothing else for you. Pay the ransom. There was no better approach, and even that did not work in some cases. But ransomware, that was a big one. We talked about DNS earlier. DNS poisoning is a way for a user to set up a malicious DNS server that will hand out false information. So I think on our YouTube channel, I think Charles has a video out there. I know he does it in one of his courses, but I think it's on our YouTube channel. Charles shows you how to very quickly, I think using Kali Linux, how you can make a page that looks like the Facebook login page. And it's really set up to capture data for people that come there. So if you had a phony DNS server set up, you could tell people, all right, come to this DNS server, or they go to the DNS server and you say, I want to go to facebook.com. They give the IP address, not a facebook.com. They give the IP address of their Kali Linux machine that looks like Facebook, and they capture your data. How would we convince somebody to point to a DNS server that wasn't legit? We've covered it in class. Pop quiz. Can anybody tell me in the chat? And there's probably more than one answer to this, but I'm thinking about something specifically that we discussed. How would a malicious user convince me to go to their DNS server? Any ideas? Chat that one in. And there's a few different things out there. One that we've talked about in class. Remember when we talked about DHCP snooping? With DHCP snooping, when we talked about switches, we said that we would only accept, or if we haven't talked about it, let me explain what it is. With DHCP snooping, we can say what port on a switch is trusted to send us a reply. Remember Dora the Explorer, DORA, Discover Offer Request Acknowledgement? When we send out that Discover broadcast saying, hey, are there any DHCP servers out there? The first one to respond is the one we go with. The first one that we receive an offer message from. What if an attacker sent up a malicious DHCP server on a port? And it was the first, a percentage of the time, it might be the first to respond to DHCP queries. And they gave us their DNS server's IP address. Yikes. With DHCP snooping, though, on our Cisco Catalyst switches, we can say all the ports are untrusted to receive a DHCP offer, except we can make one or more ports trusted that we know go to legitimate DHCP servers that we have personally administered. Now, ARP poisoning, this is clever. I almost admire who came up with this one, even though it's evil. It's very evil, but it's kind of clever. We'll talk about it in just a second. And in fact, I've got slides to walk us through ARP poisoning, so I'm going to put that one in the back burner for now. Oh, in fact, here it is. This is ARP poisoning. It's a man-in-the-middle attack that we can launch. Now, normally, we've got this laptop that goes out to the internet through its default gateway, that router on the screen. That default gateway has an IP address of 10.1.1.1. And as we talked about yesterday, it's not enough for me to know the IP address of my default gateway. I've got to know its corresponding MAC address. So what do? Yeah, I send out an ARP broadcast. I say, hey, can somebody tell me the MAC address for 10.1.1.1? And the router says, yep, that's me. I'm the all-A's MAC address. And we make a note of that. We put that on our ARP cache, so we don't have to ask again for a while. Well, what if this malicious user came by, this man in the middle as we call them, and they send us an ARP reply? It's an unsolicited ARP reply. That's why it's called a gratuitous ARP, or a GARP, some people call it. But we're going to send they send a gratuitous ARP, and that contains information saying the MAC address for 10.1.1.1 is the all B's MAC address, the MAC address of the attacker. And our computer says, oh, I'm so glad you came along and told me that. I thought it was the all A's MAC address. My bad. Thank you. I'll update my ARP table based on that. So now the computer has been convinced that to get to 10.1.1.1, it needs to send its frame with a destination MAC address to the all B's MAC address. It goes into the attacker's computer. They capture the packets using Wireshark or something like that, and then they send it on its way out to the internet. In one of the security trainings I used to do, I would set this up, and I would launch a gratuitous ARP attack against, I think I did it against my iPad. And then I would log into a site, and I would capture the packets, and you could literally see me typing in every single character in the password if it was not an encrypted protocol that we were using. So that is a man-in-the-middle attack, or a gratuitous ARP attack, sometimes we call that. By the way, how do you defend against that? Let's talk about mitigating. Let's talk about mitigating all these different network threats. I'll give you one of them, since we just talked about that man-in-the-middle attack. Cisco's recommendation to defend against that kind of thing. Actually, there's a couple of things. There's something called dynamic ARP inspection, DAI, which will defeat it. That's a really cool way of doing it. That gets it a little bit advanced. But just a simple way you can do it is shut down any unused ports. Don't let somebody come in and find an unused port in an empty cubicle and plug in and suddenly be on your network. But now that we've talked about some of the bad things that can happen, let's talk about how we can mitigate some of these threats. One thing is to keep our signature databases up to date. We know that if we have some sort of antivirus program on our computer, we periodically get updates for the virus signatures. Well, do you remember yesterday, or maybe it was 2 days ago? It's been quite a week, hasn't it? We had IDS and IPS intrusion prevention system sensors. They had not just like a virus database; they had a database of well-known attack patterns, and we need to keep those up to date. So you hear about day zero attacks. Are we going to be able to protect ourselves on day zero when a new attack is launched? So we want to keep our signatures as up to date as possible. And there are some best practices that you can follow to harden your device, is the term. When you harden a device, you're basically following a series of best practice security recommendations. Cisco has a utility that will do this for you. It's called Auto Secure. Now, I'm not encouraging you to enter this on one of your routers, because if it's not in sync with another one of your routers, its neighbor, it could stop communication. It could block traffic that you don't want to block. But if you know about all the security commands, and you can set it up during off hours, or set it up in a lab environment to be safe, you can simply type in from not even configuration mode, just from the user or privilege mode prompt. You can say, auto space secure. Press enter, and it will walk you through this interview process where it asks you all these questions. And it'll set up your router as a firewall based router. It'll set up a bunch of access control lists, and it just does lots of cool stuff. But that's an example of device hardening. Now, something we talked about yesterday when we discussed VLANs, remember we had a .1Q trunk that interconnected a couple of switches, and a .1Q trunk would assign, or it would give 4 extra tag bytes for frames belonging to every VLAN to say, you're a member of this VLAN, with one exception. The one exception was the native VLAN. The native VLAN does not get tagged. By default, the native VLAN is 1. By default, all ports belong to VLAN 1. Cisco, and we won't get into how this next works. It's a little bit more involved, but taking advantage of native VLANs, you can do something called Q and Q tagging, and you can do an exploit called VLAN hopping. Bottom line is, it's a good practice to change your native VLAN to something other than 1, where everybody doesn't know that it's a 1. What else do we have? Oh, we talked about the inside user threats. How do we protect against the inside user? Well, let's define which accounts have which privileges. The temptation is to make it easier is, okay, you're an employee, we'll give you employee permissions. Oh, I did air quotes again. I got to stop that. We got to give them employee permissions. And that might be too many for their particular job role. Well, let's do the extra work. Let's not give somebody more permission than they need. Otherwise, even accidentally, they could do something destructive. We could have software that monitors the integrity of files to make sure they've not been corrupted, like somebody trying to come in and manipulate a database. The way that we can do file integrity checking, there's software that does this, but we can run what's called a hashing algorithm on a file, and it generates basically a fingerprint. MD5, Message Digest 5, that's an example of a hashing algorithm. We could run the MD5 algorithm on a file, no matter how big it is, and it will produce what I call a fingerprint. It's a 128-bit string called a hash digest. Well, we can check, the software can check from one day to the next day to the next day, has this hash digest, these 128 bits, did they change or are they still the same? If they're different, then the file is different. And if it should not be different, that's cause for concern, and we can take action. And we talked about giving privileged user accounts. That sort of ties into this next one of assigning different roles. You might not want to say, you mean I've got to set up a separate security policy for every employee? I got 5,000 employees. How am I supposed to do that? Now, what you might do instead is assign or create security policies for different roles within your company. And for those different roles, you can say, this is the level of permission somebody working on the help desk has. This is the level of permission that an IP phone installer has. And you just come up with those different roles. You don't have to be as granular as setting it up on a per user basis. Another way to help protect ourselves and actually learn more about the attackers that are coming into us is to set up a distraction. You can set up a server called a honeypot. Remember the story Winnie the Pooh and the honey gets stuck in the tree because he wanted to get the honey. Well, the honey can attract, or the honey pot system can attract malicious users. And they're going to have these vulnerabilities that they know about, and they'll have exploits to take advantage of those vulnerabilities. So they find your Linux server, let's say, and they think, oh, these people, they forgot to apply this patch to Apache, the Apache web server. So I'm going to go in on this port, and I'm going to get root control, and I'm going to do this. And you just kind of let them go nuts on that system. You give a measly attempt at securing it, just so that it looks good. It looks like you try to secure it. But in reality, you left a lot of vulnerabilities open so that they would come in, and as they were scanning for weak targets, your honeypot would show up as a weak target. And they would take advantage of that, and they would tinker around in there. Not only would they be wasting their time on a system that had no valuable information, that would give you time to identify, hey, somebody's in our honeypot, and identify who they are, block them, or sometimes we just watch what they're doing. Let's see what sorts of exploits that they're using and find ways that we can protect against those if somebody tries to launch those exploits against our valuable data. Now, that's what a honey pot is. That's a single system. But you could be a little bit more extreme with this. You could have an entire, what's called a honey net. You could have an entire distraction network where you might have routers and switches and servers that really are not, surely not carrying meaningful data. It's just a sort of catch to attract the malicious user to either block them or learn more about what they're doing, or maybe even apprehend them. And the game of securing your network, it's really, I think of it as a game of leapfrog. It's going to be, all right, this one day the security professionals are going to win, the next day the attackers are going to win, and it's just back and forth, and there's always going to be new threats coming out. There's always going to be new mitigations to those threats, and it's hard for some companies to keep up with everything that's coming out new. So what a lot of people will do, they will hire companies to do what's called penetration testing or pen testing. In fact, I think you can even get a certification. I think maybe CompTIA has a certification. I'm not sure on penetration testing. But this is where you pay somebody to attack your system, if you can imagine such a thing. So you tell somebody that, all right, you're going to try to come in and see if you can gain control of my system or my network. And they come back a week or so later and they give you a report. All right, here's how we would rate your level of security. These things you're doing great. Here's the weakness in your firewall. Here's what we'd recommend. They give you recommendations for what you should do to improve your security. And I think it's best that you're paying the person that's breaking into your network and they're going to tell you what's going on, as opposed to having a malicious user do it. Now, here's what I was talking about earlier when I was talking about the DHCP spoofing or the DHCP snooping. Here, we've got a rogue DHCP server maybe trying to give us phony DNS information, and a legitimate DHCP server. Now, when that client sends out that discover saying, are there any DHCP servers out there? The first one to respond is the one we listen to. What if we hear the rogue DHCP server first? That could be a problem. So what we can do is configure DHCP snooping and say what ports are trusted and what ports are untrusted to receive an offer message coming in from a DHCP server. Okay, true story. This happened to me a few years ago, actually several years ago, but this could have prevented this problem that I had. I was working with a company that was providing internet access for one of those big tech conventions. It wasn't Cisco Live. It wasn't that big, but it was a big tech convention up in Cincinnati, Ohio. And the company I was helping, we were giving internet access to the vendors that set up on the show floor. You know, they set up the little booths, and you go by, and you know they give you these little gadgets, and they tell you about their product. You've been to those. Well, I get there the night before. The internet connection's working beautifully. We've got our DHCP server set up to hand out IP addresses to everybody. Things are golden. We're so ready for this the next day, we think. I get there about 7:30 the next morning as the vendors are getting set up. Pandemonium has broken loose, to put it lightly. Vendors are freaking out because they can not get to the internet. So since I was a manager of the technicians there, I was freaking out as well. So here's what happened. We thought, what is going on here? So we went to computers, and they had these weird IP addresses that they didn't come from our DHCP server. They weren't hard-coded. Where'd this come from? And pretty quickly we discovered that we're not the only DHCP server on the floor. Now, this was not malicious. At least I don't think it was. But when a lot of these vendors brought in their computers, their servers from the office to do their demos to customers, the servers that they brought in were DHCP servers. They were running that service. In fact, I think when it was over, we counted about 4 DHCP servers that were on the show floor. So when people would boot up, whoever answered first, that's who they went with. And those DHCP servers, they were handing out IP addresses that might have worked back at their office. It certainly wouldn't work at the convention. So I ran around like a madman for about an hour, just hard coding IP addresses into computer after computer. I was breaking out into a sweat. It was a bad morning. It was a really bad morning. That could have been prevented had I known about DHCP snooping. I could have said that the only port that was trusted, the only port that was trusted is the port connected to our DHCP server. Now, let's talk about not just security. Let's talk about specifically wireless security, because that seems to be more vulnerable than wired security sometimes. And with wireless security, we've got two primary goals. Goal number one is to do authentication. We want somebody to prove that they are who they claim to be, maybe through providing credentials like a username and a password. And we want to encrypt the traffic. So if somebody intercepts those packets in midair, literally, they're not going to be able to do anything with that information because it's all scrambled up. So how do we provide authentication and encryption for wireless networks? Well, we can do, let me tell you about some things that are not so awesome. We can do MAC filtering. With MAC filtering, we can, and this is very administrative intense, we can say, here is a list of MAC addresses that we will allow on our network. So if somebody brings in some other device, we're not going to allow because they're not going to have a matching MAC address. That's not super secure because with one command on my MacBook Pro, I can change its MAC address to whatever I want. Geofencing, that's kind of a cool one. What that will do, it will make sure that before a device can attach to the wireless network, if it's something like a smartphone that can be geolocated, it has to be within this geofence that we've created. Like they're not going to be in another state, another country launching an attack on us. They have to be on site in order to get to this network. But let's talk about the actual protocols that are used in wireless security. The first one, in fact, this was part of the original IEEE 802.11 wireless standard, and it's called WEP, W-E-P, Wired Equivalent Privacy. The implication with the name is the privacy or the security is equivalent to being on a wired network, to which I would say, poppycock. It is nowhere near as secure as being on a wired network. It is extremely, extremely weak. Here's the deal, to give you just a little bit of background. It uses an encryption algorithm called RC4, which stands for Ron's code version 4. Ron was one of the RSA guys. But RC4 is not a bad encryption algorithm, but it's how they implemented it in WEP that made it so bad. The way RC4 works is you have what's called an initialization vector. It's this string of 24 bits. And you take that initialization vector, and then you take a shared key that you've typed in both sides, and you take that key, and then you take that data. Somebody says, a good old WEP. And you take the initialization vector and the secret key and the data, and you do mathematical magic on it. You kind of grind it all up. And what comes out is the quote unquote encrypted, I did air quotes again, that gets sent over the air. And statistically, if you were on a fairly busy network using WEP and you could capture, I'm trying to remember the exact numbers. If you monitored that network and captured packets for about 3.5 minutes, you had about a 50% shot of getting the secret key. If you monitored for 8 minutes, it was almost a guarantee. You had like over 80% probability of determining what that secret key was, which you could then put on your device and get on the network. The reason was the initialization vector was too small. In other words, more than one string of data could create the same encrypted string. That's called a collision. Not an Ethernet collision, but it's in encryption terminology. It was called a collision. And once you had enough collisions, there was a way to mathematically determine what the key was. Yet, in just a few minutes, we could break the key with free software that we download from the internet. It's horrible. Don't use it. So what came after that? After that, there was something called TKIP. Now, TKIP, much better than WEP. It did use RC4 as the encryption algorithm, but it used a much stronger initialization vector. It used a 48-bit initialization vector instead of 24-bit. Now, well, is that double? Are we now it's now going to take 6 minutes to break in the network? No. When we double the bits, every time we go up 1 bit, we're doubling the protection. So we add 1 bit, we've doubled the protection. We've added 2 bits, we've quadrupled the protection. So it goes like, double, then 4, 8, 16, 32, 64, and just on and on. We're orders of magnitude. We're like billions and billions of times more secure just by using a 48-bit initialization vector as compared to a 24-bit initialization vector. Now, as great as TKIP is, it's not the best encryption, or as good as RC4 is, it's not the best encryption out there. Sort of the flagship encryption standard that you hear about today is AES, the Advanced Encryption Standard. So why don't we just use that? Why do we even go to RC4 again? Well, hardware. It takes more processing power to do AES, encryption and decryption, as opposed to RC4. And there was all this installed hardware. We had access points in our ceilings. We had our wireless phones, our smartphones with wireless access. We had our computers with wireless network cards in them. They were designed for WEP or TKIP, which put relatively low processor demand on encryption. If we went to AES, that could overburden the processor. So TKIP was meant to be sort of interim as we're replacing the hardware over time and we're getting better and better hardware. TKIP's going to give us, it's a lot better than WEP. It's sort of the path to using AES. And the actual standards that you heard about for years were these. And we still hear about them. WPA, that stands for Wi-Fi Protected Access. WPA was what used TKIP. WPA was used instead of WEP. When you set up, if you have an older access point that actually supports WEP, actually several still support it, you'll be able to select WEP, or maybe you'll be able to select WPA. WPA is going to be using that longer, that 48-bit initialization vector. It's going to be using TKIP. But still, collisions happen. It's going to take longer to crack the security key, but it is still crackable. So then along came Wi-Fi 2, or WPA 2. It came out, I think, around the early 2000s. In fact, from beginning in 2006, the Wi-Fi Alliance had a requirement. They said, if you want your equipment to be certified as WPA 2 compatible, we got a requirement for you. The requirement is your equipment must support AES, the more processor demanding encryption algorithm, but the more secure one. But you don't have to run it. The requirement was you've got to support it, but if you want to run TKIP, you still can. You had the option. So if you had really, really old legacy hardware that you didn't want to get rid of, you had the option. You can do this on Cisco wireless LAN controllers. And we talk about this, we actually use a Cisco wireless LAN controller next week in our CCNA course, and we show you how to set this up. But we say we can run just TKIP, just AES, or we can do both, depending on the client. And for about a decade, WPA2, it was the go-to wireless standard when it came to security. And around 2016, there was a vulnerability that was discovered. And that vulnerability made it possible, and I've read the literature on how it works. I don't understand it enough to explain. I would love to explain it to you because I love to geek out on stuff like that. It was so complex that I would not do a good job of explaining it. It was it took them a decade to do it, so it was really creative. But yeah, you can go check out the literature if you're curious, as I was. But wow, there's some heavy-duty decryption going on there. It was out-of-band decryption. I'm not going to try. But after that vulnerability, what did we do then? Well, you guessed it. WPA3 came out. And WPA3 is even better. It gives us a couple of extra protections like the AES I mentioned. Well, AES up till now had used 128 bits, which is awesome. But if we're running in enterprise mode, WPA3 is going to use a whopping 192 bits for its encryption key. Oh, now what is enterprise mode? Let's stop and define that term. If you're in your home and you're setting up your Wi-Fi network, you could use what's called a PSK, a pre-shared key. In other words, you go to your device, you type in, here's my secret key. And you go to another device, or you go to your wireless access point, and you type, this is my secret key. You type that in. They match. You get on the network. Would that work in a large enterprise, though? We got a new employee. Hey, new employee, here is the password that all 5,000 of us are using. You wouldn't want everybody to use the same password. If we had the disgruntled employee that gave it out to malicious users, or we lost a piece of equipment that might reveal it, we'd have to go change it on thousands of devices. It just doesn't scale. So in enterprise mode, what we do is we have a security server. Typically, it's called a radius server. And what we can do is give everyone their own username password combination. So before they get on the wireless network, they have to authenticate with the wireless network using with that server. And that server will give them a temporary key to use for their encryption. And that's going to be what's used to scramble things up just for that session, not for any other user, not for any other session. So if we're using enterprise mode, we even get better AES. And have you ever done this on a wireless access point? A lot of them have the that little WPS button on the back. So if you want to add a new device, instead of actually having to go into that device and say, here's my SSID and here's my shared key, you press that WPS button and it just helps the other thing magically join. I'm not a big fan of that personally, but there was a vulnerability discovered in that. So there's a replacement of that also in WPA3. And there's some other stuff too. There's it's called simultaneous authentication of equals. That's where you're not able to do a brute force attack offline. There's a bunch of stuff, but bottom line, WPA3, good. WEP, really bad. And here's a graphic of what I was talking about with the personal mode, the pre-shared key mode versus enterprise. With pre-shared key, we're hard coding this secret key into our devices manually. Doesn't scale. With enterprise mode, we're having this radius server authenticate us. So when the client connects to the access point originally, they're sent to the radius server and they're prompted for credentials, typically username and password credentials. If they provide those and they match what's in the radius server's database, or maybe a Microsoft Active Directory database that we're synchronized with, then we'll generate this session key that's given to the access point and the client. And they're going to use that session key to encrypt traffic during the session. That is a look at network security. Our next topic is on network monitoring and management. I'm just going to take a quick look. Maybe we'll take a couple of questions. If you, again, preface your questions. No need for Charles to send me anything on this one, but I'm just going to look for any questions. Preface it with some question marks, if you would, if you have any questions on network security. Let's see. Oh, I love it how you guys are kind of chatting and sharing tech tips with each other. That is awesome. Does the CCNA exam have lab simulations or troubleshooting during the exam? I've got to be really careful with non-disclosure there. I'm not able to really say what I've seen or not seen on the exam. I wouldn't be shocked if you came out and said, there were no simulations on there. I think it's possible. I wouldn't be too shocked if you said there were simulations on there. But yeah, you might not get simulations. Who knows? Any other questions? What is RSA? Somebody's asking. RSA, that's actually the name of a company, and it stands for the creators of this protocol. RSA stands for Revest, Shamir, and Adelman. And they developed something that works with PKI, the public key infrastructure. That's a really good question, actually. Let's talk about that for just a second. With the public key infrastructure, let's say that we're going to Amazon.com. And I go to checkout and I'm connected via HTTPS. So when I send my credit card information, it's secure. So what happens is you'll see maybe up in your browser, there'll be a little icon of a lock or something. It depends what your browser is. That means you've got a secure connection. Now, how is that a secure connection? It's what was originally developed by RSA, this public key infrastructure. What that means is Amazon has sent you what's called a digital certificate. Now, this digital certificate contains Amazon.com's public key. Now, we've been talking about the keys have to match. The keys have to match. Not here. Not with RSA. Not with PKI. We're using asymmetric keys here. This is where we have two keys. We have a public key and we've got a private key. And here's the rule, if you want to jot this down. Again, we've got two keys, public and private. The rule is, if I'm going to give you my digital certificate, that's going to contain my public key. I'm willing to give my public key to the public. Anybody that wants my public key, they can have it. But I'm not giving anybody my private key. And here's the rule. Anything encrypted with my private key can only be decrypted with my public key, but the corollary is more important. Anything encrypted, catch this, anything encrypted with my public key that I gave you freely, if you encrypt it with my public key, it can only be decrypted with my private key, which only I, as Amazon, have. I'm pretending to be Amazon in this scenario. So I give you my digital certificate, and you see, oh, there's Amazon's public key. Here's what you can do. By the way, asymmetric encryption, where we have public and private keys, that's about 100 times slower than what we've been talking about. We've been talking about symmetric encryption, where both sides have a shared key. They're the same. That works about 100 times faster than the asymmetric key. But we have to use asymmetric keys initially just for me to get Amazon's public key. So I take Amazon's public key, and my computer is going to generate a big random number. And that big random number is going to be our session key that we're going to use for encryption during this conversation. It's going to be a shared key. How do I get it to Amazon securely? They gave me their public key. So I'm going to encrypt this big random number that I just came up with. I'm going to encrypt it with Amazon's public key and send it back to them. Is it a problem if some malicious user intercepts that packet and they try to decrypt it? After all, that malicious user, they also have Amazon's public key. Nope, they cannot decrypt it with that. Remember the rule, if something was encrypted with my public key, it can only be decrypted with my private key, so only Amazon can decrypt it. They get my packet encrypted with their public key. They decrypt it with their private key, and they reveal this big string of digits and characters that I came up with. What's going to be used as our session key. So Amazon has it. I have it. We are now doing symmetric encryption, which is a lot faster than RSA's approach. But RSA was valuable in getting that set up. Now you might wonder, how do I know that digital certificate really came from Amazon? Couldn't a malicious user say, here's your digital certificate, I'm Amazon.com. Yeah, that's it. I'm Amazon. How do we know it's really Amazon? Because the digital certificate is signed, we call it. Signed means that it has been vouched for by a trusted third party. There are companies out there called CAs, certificate authorities or certification authorities, depending on what literature you read. The first one that comes to mind is VeriSign. You might have heard of VeriSign. They're a trusted third party. They signed Amazon's key saying, this is really Amazon. And I can trust anything that VeriSign has put their stamp of approval on. Okay, how do I know that VeriSign approved it? Well, when I say they signed it, what they're really doing is VeriSign encrypted Amazon's digital certificate with VeriSign's public key. Actually, their private key, excuse me. They encrypted it with their private key. So when I get the digital certificate from Amazon, initially I cannot read it. I see that it's been encrypted by VeriSign. In other words, it's been signed by VeriSign. It's been signed by VeriSign's private key. What can decrypt VeriSign's private key? VeriSign's public key. How do I get that? It's in your browser. When you installed your browser, you can dig around and probably find it under your security settings. You get this big, huge listing of trusted third parties, of all these CAs from around the world, including their public keys. So right now, you've got VeriSign's public key. When you installed your browser, you're going to be able to unlock, you'll be able to reveal Amazon's digital certificate containing their public key because you've got VeriSign's public key. And that's how RSA works. Wow, that was a long explanation, but I hope you enjoyed it. All right, let's get back to it. Network monitoring and management. One of the biggest things about network monitoring and just managing a network that's not super exciting to me anyway is documentation, because You got to keep it up to date. I always say having incorrect documentation is worse than having no documentation. I'd rather just go in and discover things for myself than be handed incorrect documentation that's going to lead me on a wild goose chase. And when we have documentation, here are the types of things we might have. We might have a logical topology of how things are designed in the network. Remember, we talked about logical versus physical topologies. We could have documentation for that. We need to update that every single time we install something new. When I used to be a network manager at a university, that was one of my responsibilities, to update the network diagram. So I installed a switch. Okay, get into my little CAD program and add that in. Yeah, that might be somebody's responsibility to keep that updated. And it's great to have this documentation when it comes time to do your troubleshooting or to get new employees up to speed on what's going on in the network, or if you want to do expansion. You got to know what you have now if you're going to do expansion. And here's a big one that I'm going to get on my soapbox a little bit about, and that's change management. What change management is all about is making sure that the right hand knows what the left hand is doing. In really large organizations, can you see that it would be a problem if somebody's out messing with some computers one day or some hardware, some routers, and they didn't tell somebody else in the IT department about it? So this group is seeing weird stuff and they didn't know this other person was doing it. So in your larger environments or even medium-sized environments, I'm a huge advocate of having software that will record changes that you intend to make. Is anybody running change management software? I'd love to know what it is. Go ahead and put it in the chat box if you would. But I'll give you an example of when I was at Disney World. We had been working for, I'd been working for months on designing the new network that tied together the theme parks, the Magic Kingdom and Epcot and the studios and Animal Kingdom and some of the resorts. It was called SmileNet, by the way, because it kind of looked like a smile when you drew it out on the topology. But what I was going to be using for the backbone switch, the main backbone switch and the tunnel system underneath the Magic Kingdom was a Cisco Catalyst 6500 series switch. And I had already done the design. I had pre-configured the switch, and I had to go before a review board. Remember, we talked about spanning tree design yesterday. I had to go before a review board and defend why I set up spanning tree the way I did. Why is this the root bridge? Why is this the designated port? Why is this the root port? I've done all that. Everything had been tested in a testbed environment. We were ready to go. We had the equipment there. We needed to just go in really late at night, like 2 a.m., and we were going to unplug the fiber from the old switches and plug it into these new switches, and we were going to be going from a backbone. This is many years ago. We were going to go from a backbone of 100 megabits per second to a gigabit per second. So the design was ready. The night was there, about 2 a.m. So we get, a few of us get in a company van and we drive over to, it's called the Utilidors. It's, there's an opening just kind of below Fantasyland in the Magic Kingdom. And we go in there and there's where the equipment room is. And the lights are on, everything's blinking, things are good. We unplug from one switch, we plug into the other switch, lights start blinking. We think, oh, we've got traffic. This is awesome. And we're feeling pretty good about things. Now, this was a huge change. We just ripped out the backbone of Disney World. And not just Disney was on this. I mean, it included ABC TV in New York, Paul Harvey Studios in Chicago, Disneyland. And I mean, it was a big deal. It was interconnected with all those networks. So we wanted to go back and do some verification to make sure we got it right. So we go back to our offices and I don't know, it's probably maybe 3 a.m. at this point, and we realize we got problems. Email's broken. I mean, not just locally. I mean, nobody that had a Disney.com address can get email. Everybody from Michael Eisner to Mickey Mouse cannot get email. So we're wondering at 3 a.m. in the morning, did that have anything to do with us ripping out the backbone? Kind of seems coincidental, doesn't it? So we were thinking about, okay, what's our resume going to look like tomorrow morning? But yeah, that was one of the more stressful times in my professional career. So we started trying to do some troubleshooting and everything looks good. Spanning tree is working. We got connectivity here. I can ping this. We couldn't find out what was going on. How did we break it? We couldn't figure it out. So we alerted the email team. We had a couple of email servers, which if you watch the Hercules movie, the email servers were named Pain and Panic, the little imps from Hercules movie. But we got the people that managed Pain and Panic. They came in there and they took a look, and within about 45 minutes or so, they figured out the problem. The problem was nothing that we'd done, but somebody out in Anaheim, California had replaced a network board. It was a piece of ATM equipment, asynchronous transfer mode equipment. They'd swapped that out, and they did not fill out a change management request. Now, before we did what we did, I got on the Disney change management system and I sent out things saying, all right, at 2 a.m., we're going to disconnect this. You're going to lose connectivity here. It's going to be restored within an hour. Nobody from New York to Chicago, nobody had a problem with it. Everybody's good. The people in Anaheim, they made their little swap without telling us. We had no idea this was about to happen. So it was a stressful night. They did not use the change management system. So that's the reason I'm such a big advocate of it, because it was a rough night because that was not followed. I encourage you to have change management in your company. Now, talking about the documentation still, you probably want a diagram of how the wiring runs within your building. We've talked about the wiring closets. Those are oftentimes called an IDF, an intermediate distribution frame. And those IDFs, they typically connect into what's called riser cable. And that goes down to an MDF, a main distribution frame within a network. Something else that we might want to have is we want to have some baseline information, or we want to document anything that might be going wrong on the network, and we can do that with a protocol called syslog. And with syslog, we can get error message, not necessarily error messages. There's like 8 different levels of severity that we can get messages about. And we get to say how severe of a message we want. But that's another good thing to document. It's not something we're going to review on the regular, but we can store it to a file. And if we're doing troubleshooting, that document, if you will, is in that file, and we can go examine that. We can also, probably not the syslog information, but just regular logs like change logs. We should have somebody that's going to review those periodically. And we talked about hiring an outside company to come in and do pen testing for us to see if we had any vulnerabilities. I think it's a good idea if we do some basic pen testing on our own. Here's what we can do. We can do what's called a ping sweep. You can get software for free on the internet that will do a ping sweep of your subnet, or a subnet that you specify, and it's going to try to ping every IP address on the network address you tell it, just like Matthew Broderick in War Games. And when we get those ping replies, we know, oh, there's a device on the other end. So then we do a port scan of those devices. If port 23 is open, we know it's running Telnet. If port 110 is open, we know it's running POP3. So we know the services that are running, and then we try to determine, are there any vulnerabilities that are known for POP3 running on a server? And if they are, we might try to use an exploit to take advantage of that vulnerability. Now, and then we might want to apply a patch. We want to apply a patch to something. Well, I'm thinking about Microsoft. Microsoft, I think they still have this. They call it Patch Tuesday, where they would come out with patches, security patches to their operating system every Tuesday. Yeah, we want to keep those security patches. We want to keep those up to date. And we want to also, for troubleshooting purposes, we want to be able to compare the configuration now that's not working with the baseline data, the configuration that we captured after install when it was working. And you're looking for the delta. What's changed from the time I installed it to what's happening right now? We want to be able to compare current stats with baseline stats. And it's super handy to be able to do packet captures and analyze those packets. Back in the day, when I was working at the university, it was expensive to do packet capture. We bought this network monitor thing from HP that accepted a little 3.5-inch floppy disk to store it on. I'm not kidding. It cost $40,000. This one network analysis tool from HP, $40,000. Now, go to wireshark.org, download it on your laptop for free, and you've got a very robust packet capture traffic analysis utility. In our next module, we want to talk about high availability. And high availability is making sure that our network is up and operational. And I think this is going to be our last module, by the way. So we're getting, let's see, time wise. Oh yeah, we're going to have plenty of time. But high availability is making sure that we minimize our downtime. That's what we talked about at the beginning of class today. I said I've got a redundant system where I can teach class because my normal instruction computer, it's kind of on the fritz right now. So we're using a backup system, thus the different background. But the gold standard for high availability is called the 5 nines of availability. That means that we are up 99.999% of the time. And if you do the math, that translates to about 5 minutes of downtime per year. Now, the last I heard, I saw the stats on Cisco's network in San Jose. They didn't achieve the 5 nines on their network. They were close, but and this has been a few years back, so maybe they have now. But it's tough. It's tough to get the 5 nines of availability. You know what wasn't tough to get the 5 nines of availability with? Phone systems. PBXs, they just ran. They just worked. And there was a lot of reluctance for people to start putting voice traffic on a data network. I know the director I used to work for, he said, my PBXs never go down. He said, you're taking the network down all the time. Yeah, I had a bad habit of rebooting the network in the middle of the day because something needed fixed. I hadn't yet learned the fine art of minimizing user impact, so I would just reboot a router in the middle of the day. But I've learned since then. But yeah, a lot of people had hesitation about doing that because they were more used to a more reliable network, and it's hard for the network to have the 5 nines. Now you can throw a lot of money at this and get more availability, more uptime. You can get redundant power supplies. In a lot of our modular routers and our modular switches, instead of just having one, what's called a supervisor engine, you're gonna have two. Instead of one power supply, you're gonna have two. You can have two identical switches side by side with redundant connections connecting out to your wiring closet switches. So if one goes down, the other takes over. We talked earlier about the 3-tier model that Cisco has talked about for years. And we talked about the access, the distribution, and the core layers. Did you notice? I think we might have mentioned it at that time, but notice how there's all these we've got all these redundant links built in to our enterprise network. Going out to the internet, it's great to have redundancy. If you just have one internet service provider, as we used to at the university, if they went down, we're down. There's no alternate path to get out to the internet. So what do? Well, eventually we got 2 internet service providers. And yes, we were doing BGP peering between our autonomous system and each of their autonomous systems. And we did some tinkering with BGP path attributes to make sure we preferred the faster link. So that's a whole configuration story behind that one. But yeah, redundant links out to the internet, redundant links between your switches. We talked about port aggregation with Ether channel. Yeah, with Ether channel, not only does it give us more throughput, it gives us redundancy. If one of those links goes down, even though maybe we've only got 3 links left in the Ether channel, they'll still work. You can do what's called NIC teaming on some of your high-end servers. Maybe the physical server that's running your VMware ESXi software. You might have, I know the ones I have, they have 4 NIC cards each, 4 network interface cards each. I can do NIC teaming between that and my Cisco Catalyst switch. We could also do clustering and load balancing. This is going to help us reduce the load on any single server and also give us fault tolerance. Here's what I mean by that. Let's say that I'm an e-commerce company and I've got my website running on these 3 servers that you see on screen. If one of those were to go down, is that a problem? Well, it's a problem. The server just went down. But if I've got my load balancer set up, it's going to detect that it just lost contact with one of the servers. So it's going to temporarily remove that from the pool of servers and it'll just use the other 2. In fact, we might take the server down intentionally. Maybe we need to do an upgrade. We need to add some more hard drive space to it or some more RAM. Well, I can take it down. Things keep working, albeit a bit slower. I could upgrade my server, stick it back in, and it starts load balancing again. Now, a huge topic is disaster recovery. I used to know a guy. I haven't I don't know where he lives now, but anyway, I used to be friends with the guy that I won't use the name of the company, but it was one of the major brokerage houses in the country, and his whole job was disaster recovery. So we would have conversations about, okay, what are you doing for that? You know, they had all these mutual funds, a lot of money going through their network. What do you do for disaster recovery? And because they're handling, I don't know how many billions of dollars that they were handling. Yeah, they spent a lot of money, excuse me, on disaster recovery. And one way of getting disaster recovery is to do backups. Now, we used to do backups to tape media. These days, we're typically doing backups to like hard drives because the expense of those have come way down. But we've got some sort of mass storage. We might even back up to the cloud, but we can do these backups. Now, this is where a lot of people get confused about the different types of backups we have. Let's say that I've got a server and I want to make sure that I have all the data backed up on it, so I do a full backup. That backed up every single file. And if a file gets corrupted, no problem. I got a full backup. We'll restore it. And I just got to pull out one tape or one hard drive array to restore it. But let's say that I do that full backup on Monday. Okay, now it's Tuesday. Things have changed during Monday. Now it's Tuesday. Are we going to make another backup? Or I guess we did it Monday night. Things have changed during Tuesday day. Now it's Tuesday night. Do I need to do another full backup? I mean, it takes longer to do the backup. It's going to take more media to store a couple of full backups. I don't know how long I'm going to store this, but I'm starting to eat into my storage right there. What we can do instead is take a differential backup. A differential backup is going to back up everything that has changed, only the files that have changed since the last full backup. And let's say that Wednesday morning rolls around and we realize we're missing something that got changed on Tuesday. Well, or maybe prior to that, what we would have to do if we wanted to restore everything, worst case, we would have to install the full backup and then overlay the differential backup on top of that. So differential backup, the good part is the backup happens quicker. We take up less storage media. The downside is it takes longer to restore because we've got to get 2 restorations. But some people do that. They might do a full backup on one day of the week, and for every other day of the week, they'll do a differential backup. Here's a way we can make those backups even quicker and take up even less media. We could do an incremental backup. Here's what I mean. If we were doing differential backups, we did the full backup on Monday night. We did a differential on Tuesday night, which was everything that had changed since Monday. If we did a differential on Wednesday night, that was everything that's changed since Monday. Thursday night differential, everything that's changed since Monday. With incremental, it's everything that has changed since our last backup, whether it was full or differential or whatever, or incremental. So in that case, we might do a full backup on Monday. Maybe we do a differential on Tuesday. We can do an incremental on Wednesday, and that would back up only the things that have changed since the last backup on Tuesday. We don't have to go all the way back to Monday. So it's going to be a smaller backup, and it's going to take up less storage media. That's the positive side. The downside is it's going to take longer to restore because now we're going to have to restore the full backup, overlay that with the differential backup, and then overlay that with the incremental backup. So what's most important to you? The cost of the storage media and the time to back up, or the time to recover? Now, kind of on another way of backing up a system entirely is to do what's called a snapshot. If you use something, I saw we had several people in the chats using ESXi as their hypervisor. That and some other ones as well, they allow you to do a snapshot of a machine. Now what that does, that captures the entire machine state. All the files, the current state of what's in memory, it's like a snapshot of how is the machine right now. We can restore to that state with specific processes running. Well, that's great if you want to restore an entire server, but it's not great if you need to just maybe restore an individual file. You're not going to be able to do that with a snapshot. A snapshot is going to restore an entire server to a previous state. I'll tell you where this is useful: when you're labbing something up. When I'm doing things with my collaboration servers, or when I was studying for my CCA labs, I would get something to a certain state and I would make a backup of it. or I might take a snapshot of my communications manager server. Then I would do my labbing, I'd make all kinds of changes, but then I want to practice again tomorrow. I want to restore to that previous state. I got a snapshot. I just restore to that snapshot. And now that we've talked about backup, let's think about physically, where is the new server going to live? Is it just that the server went down and we've got to, or its hard drive crashed and we've got to restore it to that server? Or what if there was some sort of catastrophic disaster to the building? The building caught on fire, or heaven forbid there was an earthquake or some natural disaster where that primary site is unusable. It has no electricity. It's got water damage. It's unusable. What do we do then? That's where we have to think about remote sites as part of our disaster recovery plan. Let's say that we've got this enterprise data center and we want to have a backup. We want to have a remote site. There are 3 types of remote sites I want you to know about. The first type is the least expensive. It's called a cold site. This is where you know where you're going to back up to. You know, if this site ever goes down, if it ever catches fire, we're going to move over here. We're going to set up shop in this other building. Here's the room. And that room, it's got power. It's got HVAC. It's got plenty of floor space to set up our racks. No computers, though. It's a big echo chamber right now. There's nothing in there. So if your enterprise data center goes down, you're going to have to populate this cold site room with your hardware. And then you're going to have to grab your backup media, get it over there, and do a restore. It's going to take a while to restore. So this is very low end when it comes to remote site disaster recovery. Let's take a step up from that, though. We could have a warm site. Now, with a warm site, not only have we identified the room that has power and HVAC and all that stuff, it's got the servers there. We bit the bullet and we bought extra hardware. We bought redundant hardware. The servers are ready to go. So if the worst happens to the enterprise data center, I just got to get my storage media over there and do the restore. Yeah, maybe full differential incremental. I got to do all that restoration, but then I'll be back in business. So that's a lot better than the cold site. But the delay that's inherent in a warm site is the time to get the backup media to that site and to actually restore from that backup media, which can take a while. So the ultimate in remote site disaster recovery is called a hot site. With a hot site, not only do we have a separate location for the equipment, and the equipment's already there, we've got a connection, a real-time connection between our enterprise data center and the hot site so that we don't even have to restore from backup. Example, another Disney, I give a lot of Disney examples, but at Disney World, the building I worked in, have you ever heard of it used to be a big thing called the Go Network. It was like the ABC Go Network and the Disney Go Network. Well, that was in the building where I worked. And massive data center with all these big computers. And redundancy was a big thing. So there was a fiber connection from my building to that room I was telling you about before in the tunnel system called the Utilidors under the Magic Kingdom. There was a fiber connection going to redundant hardware. I think it was like some sort of IBM mini computer that they were using as their web server. And it was active. So as soon as something was written to the computer in my building, instantly it went and was written under the Magic Kingdom to that backup site, that hot site. So if the worst had happened to my building, everything was still current. They would have just switched over, and those computers in that tunnel system, they would have taken over and they would have carried the load. So some different options. Again, it's a balance. Your budget versus the importance of quick recovery. All right, folks, that is high availability. Oh, I said that was our last section. Let me just do a quick little check here. Cannot believe I forgot about quality of service, because this is my favorite topic in all of networking. This is our last topic, and then we'll take some Q&A, and then we'll wrap it up for the day. And we'll give you one more opportunity to take advantage of those 5 free courses that go away after this session. Quality of service. The best definition I've ever heard of quality of service is that it's managed unfairness. Think about that. I mean, there's a finite amount of bandwidth on our network. And if I want to give better treatment to one type of traffic, I might have to give worse treatment to another type of traffic. I'm being unfair, but I'm managing it. I'm prioritizing which traffic is more important to me. And that was a huge deal when we had a lot of congestion on our networks back in the day. But these days you might argue, Kevin, I don't need QoS because I've got fast networks. I've got gig links. I've even going out to the internet on fast Ethernet. I don't need QoS. You still might. Look at that top example. Yeah, we're going out to the IP WAN at a respectable speed of 100 megabits per second, but we're coming in at a gig rate. That's still a 10-to-1 speed mismatch. We're sending data into that router 10 times faster than we can send it out. That's going to cause congestion. What happens when congestion happens? Well, here's the glass I've been drinking my Coke Zero out of. There's going to be some storage space in your router called a buffer or a queue. And if it's receiving data faster than it can send it out, this queue is going to see. I thought I had a Coke in here. I could pour it in, but it's going to start to fill up and fill up and fill up. But it's only so big. It's going to start to overflow after that. So that speed mismatch could cause us to drop traffic. Even if you say every single link in my network is gig speed, you could still need QoS. Take a look at that bottom example. We've got a switch acting as an aggregation point. We've got all these servers in a server farm. They're coming into the switch at a gig, but we're leaving the switch at a gig rate. The switch is theoretically capable of receiving up to 3 gig of traffic coming in that's trying to go out a 1 gig link. That doesn't add up, folks. So the switch, it's going to have buffers, it's going to have queues, and we need to set quality of service to prioritize who do we send first. Now, big point here. I don't want you to think that QoS is a fix for needing more bandwidth. QoS is fantastic when we have periodic congestion. Just occasionally we're congested. Hear me on this. If you're congested 24/7, you need more bandwidth. QoS is not going to do it for you. But if there's just a couple times a day, maybe there's a network backup going on, or everybody's getting into the office at 8:30 in the morning and firing everything up, and there's a burst of data then as people are downloading things. Yeah, that's where quality of service could help us out. And quality of service is not a single mechanism that we just flip the switch and turn it on. Quality of service, or QoS, it's a collection of mechanisms. And I want to give you some categories. The first category is classification and marking. And as a metaphor, notice the airline boarding ticket on screen. As a metaphor, I think about when I fly, I typically fly Delta. I'm one of their Sky Miles members, but I teach online. I don't fly that much. And I haven't yet earned that status. What do they call it? Is it like silver medallion or something like that, where you get to get on the plane early? I'm not there yet. Maybe one day. But can you imagine that the day arrives where I become a silver medallion member, and they say, now boarding silver medallion members, or whatever they call them, and I go up to the gate agent and I say, hi, I'm a silver medallion member, and they say, Mr. Wallace, before we allow you on the plane, we need you to prove that you really are a frequent flyer. We need you to produce the boarding pass from the time that you went to San Diego, and the time you went to Houston, and the time you went to Orlando. Can you imagine that? Me having to prove every single time I try to get on the plane that I really was a frequent flyer? That's not efficient. So what do they do instead? If you look at the boarding pass, they actually put a stamp, a mark on the boarding pass that says something like, I think it says something like Sky Priority on it. That they can look at that marking and immediately know that I get priority treatment, or one day I'll get priority treatment maybe, and I get to get on the plane first. Well, it's the same thing with our data. Cisco recommends that we classify and mark our data as close to the source as possible. Here's what I mean by that. As the traffic is coming out from the PC, from the phone, as soon as it hits that first switch, we should classify it. We should identify, oh, this is a voice packet. This is some other packet. We should identify what kind of traffic it is and give it a marking, like a numerical value. And we talk more about this in our CCNA course. We get into the called differentiated services code point markings. There's a lot of math behind that, but just understand we're giving it a marking. It's like putting a rubber stamp on it. And that marking is going to be like that marking on my boarding pass. that packet can then present the marking to the next router and the next switch along its path. And that next switch or the next router, it can very quickly, very efficiently look at that marking and make a decision, like a forwarding decision or a dropping decision based on that marking. So we want to classify and mark as close to the source as possible. But classifying and marking by itself doesn't change the it doesn't change the behavior of our traffic. We've got to have something else that's going to take a look at that traffic and make a decision based on that marking. A classic one is queuing. With queuing, remember my glass here? To begin with, the router has one queue, one buffer, one storage area where it's putting all the packets in. But if it fills to capacity because I've got this big data burst on the network and it starts to overflow, I'm throwing away traffic. I'm throwing away all kinds of traffic. I mean, if I've got a voice packet or a video packet trying to come into that queue and it's full, there's no room in the queue. So we're going to discard it. And that can be bad for our high priority traffic. So what if I took this glass and I split it between, I wish I had a couple of the glasses here, but imagine I split it between a couple of smaller glasses. I have these sub queues now. And let's say that we put, like you see on screen, those buckets, those are sub queues. We're putting voice traffic in one bucket. We're putting everything else in the other bucket. So if there is a big data burst on the network and that best effort bucket does start to overflow, it's not the end of the world because the voice bucket, the VoIP bucket, it's not overflowing. We're not dropping voice packets because we've done queue separation. That's called queuing. If you want to put in your notes, the two primary queuing mechanisms that Cisco uses today, they're called CB-WFQ. CB-WFQ. CB-WFQ, that stands for class-based weighted fair queuing. Class-based weighted fair queuing. That can give us bandwidth guarantees for different traffic types, but it doesn't really give priority treatment to anybody. I mean, when I'm thinking of when I was in California one time with my family, we rented a vehicle, and by the way, not a fan of driving in LA traffic. I'll tell you that right now. But they had all these lanes. But because there were two or more people in this vehicle, we got to go over into this carpool lane. I think they call them like an HOV, a high occupancy vehicle lane. And I kind of felt guilty. We got all this traffic kind of standing still. We're just zipping by in this carpool lane. Well, that's what we can do with a priority queue. With a priority queue, we can take voice or video and we can stick it in that priority queue, and it kind of gets to pass everybody else up. We send it first. And that queuing mechanism for your notes is called LLQ, or low latency queuing. So queuing, it's going to be able to look at that marking, decide what sub queue to put it in, and then give different bandwidth amounts to those different sub queues. Beyond queuing though, we might want to not guarantee an amount of bandwidth. We might want to prevent this thing from filling up to capacity. If this thing fills up to capacity and starts to overflow, bad things ensue. It's not bad enough that we're just dropping all incoming traffic. Remember when we first talked about TCP? Yeah, if we talked about this, TCP, oh yeah, we talked about it being reliable. We said it uses a three-way handshake. I send you a synchronization message, a SYN, S-Y-N message. You send me a SYN ACK, and I send you an ACK. After that, you send me a segment, and I send you an acknowledgement saying, got it. And you say, oh, that worked. I'll send him 2 segments this time. Got him. Then you'll send me 4 and 8, 16, 32, 64, 128, and on and on and on. We're changing the window size. It's more efficient to send data in a single segment rather than waiting for an acknowledgement. We don't want to just send and wait. We want to send a bunch of data, and then occasionally we'll get an acknowledgement. If we miss something, we'll send it then. But that's called a sliding window. And here's what happens. When your queue fills up and you start to drop TCP traffic, they go into those flows go into something called TCP slow start. Here's what that means. Their window size, which may be 5,000 packets or so, 4,096 packets at a time, you drop they get dropped, and the sender realizes I'm sending too aggressively. So it's going to drop that window size way down. Not a big deal for a single flow. That's just the way TCP works, but your queue is full. every TCP flow is being dropped. Every TCP flow is simultaneously going into TCP slow start. There's a term for that for your notes. It's called TCP synchronization. That leads to an incredibly inefficient use of bandwidth. What's the fix for that? The fix is congestion avoidance. And the tool that Cisco uses for your notes is called WRED. WRED for weighted random early detection. And with weighted red is the way we pronounce it. And I compare it to my favorite Star Trek movie, hence the live long and prosper symbol on the screen. Did you ever see the Star Trek II? That's an older one. Star Trek II, The Wrath of Khan, with Ricardo Montalban playing Khan. Do you remember that one? Well, spoiler alert, by the way, if you haven't seen it in the past couple of decades. Toward the end of the movie, Khan has damaged the Enterprise. And he's about to blow his ship up, and it's right next to the Enterprise. It's going to destroy the Enterprise, and the Enterprise's warp drive is damaged. They cannot get away in time. So Spock goes down into main engineering, and he goes in here and he fixes the warp drive. But to do that, he had to go in this room that was full of radiation, and now he's dying very quickly of radiation poisoning. And they call Kirk up on the bridge and saying, "Better get down here." And Kirk goes down there, and he goes up to the glass and he says, "Spock." And Spock goes to the glass and he says, "Don't grieve, Admiral. It's logical." Or actually, he says, Spock says, "Ship out of danger." And Kirk says, "Yes." And he goes on to ask him, "Why did you do it, Spock? Why did you give your life to save the Enterprise?" And Spock says, "Don't grieve, Admiral. It's logical. The needs of the many outweigh the needs of the few." And then Kirk says, "Or the one." That's what weighted red is doing. Weighted red is saying the needs of the many outweigh the needs of the few. So what weighted red will do is, as our queue starts to fill up, it's going to have a marking somewhere called a minimum threshold. And if we cross that minimum threshold, we're randomly, occasionally going to start dropping, not everybody, we're going to start dropping some traffic in an attempt to keep this thing from completely filling up. We'll have this minimum threshold, and then we'll have a maximum threshold. After we exceed this maximum threshold, then all that traffic gets discarded. And you might say, isn't that the same thing as everything flowing over? No. The way Cisco does it, remember the markings we gave? The different markings can have different thresholds. So we could be discarding all of our network gaming traffic while we're not discarding some of our other traffic. That's weighted red. We also have a way to set a speed limit on the maximum amount of bandwidth that our traffic can take, or our traffic can use. And the reason I'm showing a bowl of soup here, it reminds me of that the Seinfeld episode, where if you don't order the soup correctly, the guy says, "No soup for you. Come back 1 week." You remember that one? Well, that's what policing does. If we set this bandwidth speed limit, and if we've got traffic that tries to exceed that bandwidth speed limit, literally policing says, "No bandwidth for you. Come back." Literally come back, meaning retransmit. That's one way of setting a speed limit. Another way of setting a speed limit is called shaping. Shaping is the kinder and gentler way. It's the kinder and gentler way of setting a speed limit. If we try to exceed that speed limit, shaping is going to say, "I'm so sorry. I just don't have enough bandwidth to send you at the moment. But don't go anywhere. Just sit here in our waiting room in this queue, and I'll come get you when there's bandwidth available, and then we'll send you on your way as quickly as possible." We get a lot better customer service from shaping. So shaping is going to delay us by just keeping us in that waiting area, while policing is going to say, "Nope, you're out of here. Go retransmit. Try again." Those are ways that we can set a speed limit. And finally, we have link efficiency. Link efficiency tries to make the most use out of relatively low-speed WAN links. And honestly, this is not as big of a deal as it used to be. So instead of giving you my full link efficiency explanation, I'm just going to say about one link efficiency tool. Let's say that we had a fairly low-speed WAN link. And I know in some installations, just depending on where you are in the world and what's available, how far away you are from major cities, no shame in it, some people cannot get fast links. If you have a slower link and you're trying to send voice on the same circuit that you're sending data, you might want to consider this. Imagine the scenario. Notice I'm showing a truck on screen. Now, I wasn't able to find a good picture of a triple tractor trailer. I'm just showing you a double one. Have you ever seen these on the road? You've got the truck and then you've got the three trailers behind them. I think they're called LCVs for longer combination vehicles. let's imagine that we're in our little tiny sports car and we're sitting behind one of those big triple tractor trailers and we're at a traffic light. And the traffic light changes to green and the first trailer goes through and the second but the time we get up to the traffic light, it's turned red again. We were adversely delayed of getting through the intersection because of this big payload in front of us. That's what can happen to our data and our voice specifically on low speed circuits. Imagine that traffic light is like and that intersection is like the interface on a router. And that big triple tractor trailer, that's like a big old hacking data packet, one of those 1500 byte packets. And our voice packet, it might be a little tiny 64 byte packet. It's really, really tiny compared to the big data packet. But if we're on a slow speed link, it's going to take so long for that massive data packet to get out of the interface that it's increasing delay for the voice packet getting out of the interface to the point where it could really harm our voice quality, make it really, really bad, in fact. So what could we do? Well, back to our metaphor, what if we took that triple tractor trailer and instead of just having one tractor, I guess we would call it, pulling those three trailers, what if we put each trailer behind its own tractor? So now instead of having one big vehicle on the road, we've got these three smaller vehicles. Well, I'm in my little sports car. I'm nimble. I'm agile. I can weave in and out. I can get ahead of some of that traffic, and I can get through the interface sooner. Same thing with our voice and data. By using a technology called link fragmentation and interleaving, or LFI, what I can do is take that big data packet and bust it up. And then, just like I'm shuffling a deck of cards, I can shuffle in those little tiny voice packets in amongst the now fragmented data packets, and the result is the voice packets get through the interface quicker. That's a way to make the most efficient use of a relatively low speed link. Now, I'm talking really low speed. For that to really be effective, your link speed needs to be on the order of 768K or less. But some people have circuits in that range. You might want to look into link efficiency mechanisms. Now, we finally wrap up our final technical module. I want to take your questions, but I won't go through all the bullet points again. We did that a couple of times already. But I just want to remind you that next week, if you've enjoyed this 3 days of immersion where we've just, I hope you got a lot of value out of it, but honestly, this is kindergarten compared to actual certification training. Like you can start going down the track next week. And if you would like to sign up, we've got lower prices than ever, depending on your level of commitment, depending on your career goals, depending on your budget. We've got something for you no matter where you are. And I've already gone through all these. We're going to be donating meals on your behalf when you buy any of these because we believe in giving back. And you're going to get a ton of bonuses with the executive and the diamond membership. But I said as an extra bonus, because our mastermind that I was so excited about, it's full. It filled up before today's class even started. So I want to do something else for you to entice you. If you'll sign up for the executive admission or the diamond admission, I'm going to give you five extra courses. 5 extra courses. We're going to give you Anthony Sequeira's BGP course that he did just for us. We're going to give you Michael Shannon's cloud computing course that he did for us. I did the CCNA IP subnetting simplified. I did the OSPF and the spanning tree protocol crash courses. It costs nearly $300 if you go buy those from our site right now, which you can do. You can go check it out. We're going to give those to you for free if, here's the requirement, yes, I do want to create urgency because I don't want this opportunity to pass. You know if it's right for you right now or not. You're not going to know anything different an hour from now. So, no kidding, after class, I'm going in and I'm deleting these five bonus courses from the executive and the diamond offers. So if you want to sign up for executive or diamond level, do it now, because after class, I'm going in, I'm deleting those. If you've already signed up, you've got them now. I added it to everybody's account before class that already bought. So just want to make sure that you're aware of that. Again, the links to do this, well, I'll put the links on screen in just a second. We're about to do our giveaway though. So I imagine Charles has emailed me the winner of today's book giveaway. I'll check that in just a second. But we're giving away the full set today. We're giving away Todd Lamley's Part 1, Cisco Networking Technologies, and the study guide. I'm going to be going to the post office tomorrow to get these shipped out. So I'm not sure if I'm not sure what kind of shipping I'm going to use. When I ship internationally, I know it typically takes longer. I fill out a customs form, and so if you're international, it'll get there eventually, but it typically hasn't been super quick. If you're within the U.S., it'll probably be just a few days. But here are those links. Again, general admission, if budget is your primary concern, you don't get a replay of next week's class, but you get a replay of this week, and you get to network with people that are committed to getting their CCNA certification, and you get to attend live, just attend live, and let's see, Charles just texted me the winner, but you get to attend live and take some great notes. All right, today's winner is Edgar Olvera, Olvera. Edgar, congratulations. You have won our grand prize. We're going to be sending that out to you in the mail tomorrow. So sometime tomorrow, I'll put that in the mail. And I don't know if I'll get tracking information or anything like that, but that'll be put in the mail tomorrow. Congratulations. Hey, and let's take a look at some questions that you might have. And again, just a few more minutes, literally, until those 5 bonus courses evaporate. So let's see what questions we have in the meantime. Let's see. Okay, not a lot of questions that Charles has noted. Let me go ahead and put any questions in you might have now. Somebody says, Leanne says, Kevin, what's up with that coconut water? I actually saw some last night and bought it, and watermelon. Yeah. The Bai drinks, on a side note, since you asked about it, BAI, I love those if they're coconut water. They also have like fruit drinks like watermelon. Oh, I cannot stand those. But if they're like the coconut base, they've got the pineapple coconut, love those. The lime coconut, that's pretty good. But yeah, any of the coconut stuff, big fan of that. Let's see, any questions? Any questions? Go ahead and put some question marks in there so I know it's a question for me. Somebody says, can you extend the replays till tomorrow, pretty please? Yeah, we'll extend them tomorrow. Yeah, when I said they're being taken down tomorrow, I didn't mean like early tomorrow. It'll be, here's the way it's probably going to look. I'm going to be, my wife and I are going to be on the couch. We're going to be watching like season 3 of 24 on Hulu. And we'll say, about time to go to bed. Oh yeah, I got to do something real quick. And I'm going to go in right before bed tomorrow night, and I'm going to just delete those from YouTube. So yeah, they'll be up for 24 hours plus. So now is the time to binge watch those if you want to. But remember, if you sign up for one of these courses, you get them. You'll have them today. As well as I'm putting in PDFs of the slides. So regardless of which level you sign up with, you're going to have today replays of all 3 sessions this week and the slides from all 3 sessions. Oh, lots of great thank yous coming in. I love it. Let's see. In ACL's access control list, what is considered an incoming interface, the server or the client? Yeah, ACLs, wow, that's another thing we're going to be doing in depth next week. But an access control list, we talked about that briefly. We referred to it as a packet filter one time. That says what traffic is allowed to come in or go out of a router interface. And you can apply it in the incoming or outgoing direction. And that's a very good and common question you're asking. And the answer is, what does in and out mean? In and out is from the perspective of the router interface. So be the router. You're the router interface. If you're going out of the router, or if you're sending a packet out of the router and you want that access control list to act on a packet that is leaving that interface, you're going to assign it in the outbound direction on that interface. If a packet is going to be coming into that interface, remember, you're the interface, you're the router. As traffic is coming into from some other device, whether it's local or remote, doesn't matter. But if it's coming into that interface and you want to apply an ACL to that, you want to apply that ACL in the inbound direction. Great question. Let's see. Any other questions? We've had some great ones here. Thanks for these 3 days. Oh, somebody loved Leanne loved the watermelon. Oh, see, oh no, Leanne says not a fan. Yeah, me either. I love watermelon, but not that. Let's see. Somebody says, what about quality of service protocols? Do we have actually any protocols? There's not really a protocol per se that will be spoken between devices to signal how protocols work. The one exception that I can think of is RSVP, the Resource Reservation Protocol. That is a protocol that will reserve traffic and you can communicate between devices. We normally don't use that for most of our purposes, and it's really a collection of tools rather than a collection of protocols. All right, I think that about does it, folks. I want to give you a sincere congratulations on completing this. I know that there are the many who talk and the few who do. You actually, for those of you that stuck with it all 3 days or the majority of it, my hat's off to you, because you really invested in yourself. I think we're kindred spirits. That means a lot to me. And if you entrusted me with that much of your time, I mean, that honestly touches me at a very deep level, that you would give that level of trust to me. I hope I have been a good steward of your time. And regardless of your decision on whether to take the next step with me or not next week, I hope you gain tremendous value out of this. And I realize that a few people may have paused the video to walk away from if they're watching on YouTube, so they might be like just a few minutes behind here. And I said I was going to take those 5 courses out right after class is over. Tell you what, I'm gonna set a 5-minute timer. I'm gonna do it after my 5-minute timer expires. That'll allow me to step away and take a little break. But yeah, in 5 minutes, those 5 bonus courses go away. So I'll leave the links up here for 5 minutes. Thanks, everyone. Hope to see you in another training event very, very soon. Take care, everyone.